రిజల్ట్ వచ్చిందా?
Dr. Dennis. Sorry, I just joined. Good afternoon, everyone. Am I kind of heard? Can you hear?
Hi.
Yes, sir.
So let's get everyone to have their videos up.
Yeah. Good afternoon, Dr. Hi, thanks for joining us.
Hi, Dr. Sandeep. Good afternoon.
Yeah. Good evening, sir.
Good evening, everyone.
Yeah, I think we are. Just give 1 minute. I mean, I think people are rushing in. Since we have a slightly packed day, I will not lose time. I'm sure most others will join very soon. So let's start. Good afternoon, Dr. Dennis. Good afternoon, Dr. Sandeep Grover. Thanks for joining us. As planned earlier, we have two main sessions today. The first one is on the correlation regression statistics that Dr. Dennis Xavier will continue with, and it will be followed by it's somewhat related to statistics, but looking at data acquisition, all the common measures used in behavior And so Dr. Sandeep Grover will kind of give us an overview on the statistics associated with questionnaires, rating scales, and interviews, which kind of decide how we go about choosing them for our study. So those will be the two main events for the day. I need to disappoint all the trainees. We had actually planned to have a research quiz to start with today. I think after having a discussion with Dr. Dennis and recognizing the amount of information sharing and discussion that's likely to happen today, we have chosen to postpone the research quiz to the next session. I'm really sorry we could not inform you on time. I hope it's helped you anyway have a quick revision of statistics. That was not planned at all. It just happened like that. So all of us have benefited in the process, I'm sure. So
simply pick them up out of the streets and kill them.
Yeah. Okay. So let's start the day then. I mean, I think most of the participants are here already. So maybe a few more will join, but I would think in the interest of time, let's make a start. Professor Dennis Xavier, invite you to continue on with your the session related to statistics. Thank you so much. Thank you.
Right. Good afternoon, everyone, and hello. Special welcome to Dr. Sandeep, who's joining us for the session. And as I keep telling you all from the start, I've not done any research work of my own in psychiatry, and the data and how they are dealt with in psychiatry is quite different. So that's why we have another faculty who is familiar and has done personal work in the area they add to it. Dr. Ashok, just remind me, when will Dr. right? Who will be joining us, the statistician from psychiatry background?
That's the next session, Dr.
Next week. Okay.
Yeah.
Right. So that will be kind of nice. Now that we'll be concluding all the parametric tests, and then we'll have his, Dr. Tenarasu, right? Once he joins us, then we can, get a little more insights into, the additional or the specific nuances of, psychiatric research. Okay,
Dr.
so
Dennis,
today,
Dr. Dennis, if I can just add, because that session is specifically titled, one part of that session is working with a statistician. So that's where he'll be joining. Yeah, sure.
Right. So maybe as we do in the past, Dr. Ashok, it'll be good to have a midweek discussion with him.
Sure, certainly.
We are first to see so that he knows what we have done and the approach that we have taken so far, and from there it would be useful. Okay, so today we are in for some heavyweight statistics. With the Olympics ongoing, we get some language from there. So today is heavy statistics, but as always, I'll try to simplify it. You will see equations, you will see formulae, etc. But I will try my best not to go into that. And as I keep giving you this analogy, and where is my friend who always, I think that is, I am not able to, Dr. Smita, okay. Is she there?
Yeah, Dr. Smita Ramdas is there.
Yes. Remembered my analogy of the car. Sorry, Dr. Smita, maybe you were making coffee for yourself and I pulled you out. Right. So yes, today we'll learn, Dr. Sandeep, this is what we started off with in statistics, that we will, if you need to get to point A, from point A to point B, there are various ways in which you can do that. You can sit at the back of a car and go to sleep, and then you'll reach point B, and you may not know it is point B. That's what we do sometimes. Take the data at the end of it and go dump it on a statistician. Do something and give me some p-values that I can write about. Right? You don't know what happened. Like in Hindi, they tell, no, ye kya ho gaya? Or you have no clue of what has happened. On the other hand, you can sit in the front seat, keep your eyes open, and see where you're going. That means, working with the statistician. And if you have to do, and if it is a one-off thing, that means if you're doing that for your, thesis, and you never want to do research in your life, maybe that is a good option. But still you're aware, where was point A and where you reached point B. But on the other hand, if you need to do research on a more regular basis, it's better to learn car driving rather than depending on a statistician. And of course, when I say learn car driving, we have to learn how to, not only move the car and then control it, but also be able to figure out what is there on the dashboard. When does the oil indicator come on? When does the fuel? Of course, fuel is the first thing, right? And when the battery is going low, or any other electronic these days, even simple cars have a lot of electronics. And you must also be able to change a car tire. But should you be opening the bonnet and pulling out the engine to figure out what is wrong and putting it back? Not for doctors, right? So not for us. Although I do know that some doctors are really, I know some physicians who have actually, oh, by the way, I don't know if I told this group at McMaster University, where I trained about 15 years ago, doctors take detailed courses in statistics. They're just so interested, right? They do 6-month courses on regression. They do 6-month courses on survival analysis. They are so keen and interested. And I've found some really, not for me. I said, no, I'm not going to go at that level. But one of the first things that I did when I came back is, wrote grants so that we had enough money to employ a statistician. So today we will learn how to, maybe even change a car wheel, tire. We may open the bonnet, but we will definitely not open the car engines to meddle around with it. So when you see formulae, and when you see equations, whatever is relevant for us, which helps us with clinical what should I say, interpretation, I will highlight it. But otherwise I'm going to just skip it. Now you may ask, why did you put it there in the first place? Just to give you an idea. Okay, this is what is there, and we will not go into what is there in the numerator. Occasionally I will tell you what is numerator, denominator, why this is squared, why this is why you take a square root. All of that is mathematics, which we need not worry about, right? So with this, let's go into regression. That's what we are here for today. Give me a second to pull up my slides. One second, please. Okay. Right. So can you see my slides, and is the audio okay? Can one of you all confirm, please? Okay, great. So Dr. Sandeep and Dr. Ashok, I may pause in between somewhere and tell you, can you give an example from psychiatry here? So my examples are always cardiovascular and diabetes and whatever, which we keep working about all the time. And some of them are my work. Some of the work that I'm familiar with, I will share. So I have deliberately not threaded on to examples from psychiatry. So Dr. Ashok and Dr. Grover, please be please help us by giving examples from psychiatry. Okay, so with this, let's get started. And we have a long session today, right? So we're going to do the definition of regression, the types and application of regression, look at simple linear regression, multiple linear regression. We look at one project. Actually, these are real data from our department, which we had looked at. So can I predict HbA1c from some data that I already have? So we look at that, and how accurate are those predictions? How does it work? And if there is an error, why there's an error, we look at it. And then let's look at the order of entry of variables in our models. You may be wondering what this is, but I'll explain to you what is the meaning there. And then let's look at another project looking at the effect of BMI on diabetes control. Does increasing BMI have anything to do with diabetes control? Then let's, after we do linear regression, we'll do logistic regression. We'll start with simple logistic regression, multiple logistic regression, and a simple principle for sample size and regression analysis. I'll just give you a principle. This is not the details of how you calculate sample size. We'll do that another time. And then, of course, we will summarize. So this is a fair amount or quite a bit of heavy statistics today. So tighten your seatbelts, and here we go. Okay, so what is regression? It's a statistical evaluation for describing a relationship between a dependent and independent variable. Once again, let me tell you that the independent variable is on the x-axis, right? As this increases, what happens to the dependent variable, which is on the y-axis, right? That's what we'll be looking at. So we need to get this. Sometimes we get confused. So again and again, I will remind you of that. So we'll also like to estimate the dependent variable from independent ones. If I have a bunch of independent variables, can I estimate the dependent variable? Wow, wouldn't that be nice? I have a bunch of data and there is an unknown. Can I predict that? Can I estimate that unknown? Can I also predict risk factors which influence outcomes, right? So in other words, individual prognosis determination is something that we can also do with regression. And regression goes into multiple, applications. And in a way, although today you may get bogged down by some of the equations and the formulae that you see, but I would urge you not to get worried. Don't worry. I will highlight a few things. and when I'm highlighting a few things, I will request there Dr. Ashok or Dr. Sandeep to give us an example from psychiatry now itself. So I'm sure they will have ample experience from their own data, which they can quickly share. Okay, so types of regression and its applications. So we have linear regression, we have logistic regression, Cox regression, and Poisson regression. So today we will do these: simple linear, multiple linear, simple logistic, and multiple logistic regression. The independent variable can be continuous or categoric. The dependent variable is continuous for linear, is dichotomous for logistic, is survival time for Cox regression, and count data with temporal sequence for Poisson regression. Right? Application: linear regression, we describe a linear relationship. If one increases, the other one, does it increase or decrease? Logistic regression, predicting probability of belonging to either of groups. Remember, this becomes dichotomous, yes or no, alive or dead, with a relapse of schizophrenia or no relapse, right, with control of diabetes or no control of diabetes. And Cox regression is for survival analysis, modeling survival data, and Poisson regression is for modeling counting processes with time kept in mind, or with a temporal sequence. We'll not be doing these two. We'll be doing linear and logistic regression. Okay, so as in all statistical approaches, we have assumptions, right? So assumptions for regression, that the observations are independent and the dependent variable must be random, right? And for hypothesis testing, the dependent variable is normally distributed and the variability should be the same for each value of the independent variable. So these are assumptions, and in certain situations, and this is for statisticians, they will see whether any of these assumptions are violated. If they are violated, they will tell you we need to do something else. And I will tell you, when I'm doing logistic regression, I will tell you, okay, we cannot do simple linear or multiple linear regression for this reason, and therefore we are doing logistic regression. I'll explain that to you, right? So simple regression, that the assumption we make is that the relationship between the two variables is linear. Relationship is linear, and that's how we proceed further now. Okay, so something really fundamental. You would have done this in school and college. In mathematics, you would have done it. In pharmacology, we do that for pharmacokinetic modeling. But here we go. Equation for a straight line: y equals a plus bx, right? Where y is the dependent variable, right? And x is the independent variable. A and b are calculated, and a is the y-intercept and b is the slope or the gradient or the regression coefficient. Let's look at a diagram now. Simple, right? So this is the x-axis, this is the y-axis. As x increases here, y has also increased, right? Now this is the y, this is a, which is the y-intercept, right? This point. And with change in x, there is so much of change in y. So much of change here, right? There is so much of change in y. This is the slope. This is the slope now. Oops, sorry about that line. This is the slope, and it's given by this equation. You're going to see this with real examples a few more times now, right? So this is a fundamental and a simple diagram that I want to show you right now. So how do we calculate A and B? Is calculated by the methods of least squares, and you will remember this from ANOVA that we did briefly. We did discuss this, right? So this methods of least squares calculates or finds the values A and B that minimizes the sum of squares of all the deviations or the residuals. Now you're wondering, what is deviation, what is residual? It's coming in the next couple of slides. All right. So please keep this in mind. A fundamental principle over here, right? So there is A over here, right? And B is this change or this increase for a given change in X, this change in Y for this given change in X. That being said, right, that's what I explained now. Let's go to some real examples. You'll remember when we did correlation that urea levels correlated with age. So let's do regression for the same thing, right? We are doing sum of squares. But don't worry about whatever is written here. Just follow this blank over here. Step by step, I will explain not once, I will explain this twice. So we are looking at the relationship between urea levels and age, right? So once again, just ignore whatever is here. So please follow me and follow my pointer. I hope you can see that well. So what do we have now? We have age 20 to 40, age is doubling, right? And this is urea levels increasing, right? Increasing urea levels. And these are all the dots for each of those participants or subjects who provided samples to calculate with which we estimated the urea levels. What do we see now? Right? We see it scattered all over the place, and you see a line going across here. So this is the regression line, as we call it. So let's go about it step by step and slowly, right? This is the regression line that has been drawn. And of course, we can do it manually, but now for each point, we can calculate. Probably some of you did this in school and college, looking, fitting the line, right? So Y bar is the mean urea level. Mean urea level, right? In the sample, right? YI, right, is the actual urea level. Is the actual urea level. You got it? For patient I or participant I or the ith patient, as they say in algebra, right? And what do we have here? We have Y hat I. This is the actual one. Y hat, right, is the fitted value. I'm pulling it from here to here. I'm drawing the regression. Actually, this value is here, but I'm drawing the regression line. And you see, deliberately, I've taken a wide example to show you. Is the right fitted value for the ith patient. Are you able to get that? Right? And then Y bar, okay, I told you, this is the mean of the actual values, right? Yi minus Y hat I is this one, right? So, Yi minus Y hat is the residual. This is the residual that we're calculating, and and this is the total residual. Yi minus Y bar I, right, is the total. Sorry, is the total residual, and this residual from the mean Y hat I minus Y bar, right, is our. Here we have that. Here, this is the squares of the regression. This is the sum of the squares of the regression. Okay, we're going to do this once more with another example, right? Where we were looking at BMI and HbA1c. So you'll get another exposure to this as well. So for now, if you tell me, Dr. Dennis, stop all this. I hate equations. I hate numbers. I don't like any. What are we trying to do? Bottom line. Or in Hindi again, if ye kya ho raha hai batao mujhe, right? So give me the sum of, or give me the essence of this. Essence is, we have a sample, we have the mean, and we see that with increasing age, urea levels are also increasing, right? And we have a scatter plot. We draw a regression line, and we find that the actual value is somewhere, but the regression line is fitted that value, right? It's fitted that value, and those are the equations. This is the sum of squares regression, and this is the sum of the squares of the residual, right? So regression and residual both are taken into account here. So this is the difference from the mean, right? So even though we fitted this line, it is different from the mean. This is the actual value, but I fitted it here, and this difference is here. So this is what is happening, right? We've drawn a regression line, and we are giving new points to the actual points, but we are accounting for all this. We are accounting for all this mathematically. All right. So I've taken sufficient time with this, and I'm also telling you we're going to look at another example. Moving on, we look at the coefficient of determination now, right? Proportion of the variance in y explained by x, which is the independent variable, and this is denoted by capital R square now. Capital R square, you'll remember the small r square which we did last time. So it is the ratio of the regression sum of squares with the total sum of squares, and this value is calculated by ANOVA, right? And this is the output you will get in SPSS, right? So this is the regression, and this is the residual sum of squares. Now, if I calculate R square now, which is 1.4, this is for you'll remember from correlation that we did, the change in urea levels with age, right? So I have this ratio here, 1.46 by 3.8 gives me 0.38. How do I interpret this 0.38? 0.38 tells me age account. This is where you have to pay attention. Age accounts for 38% of the total variation in urea levels. And if you recall last time, urea levels were not normally distributed, and therefore we transformed it to log normal urea. So after my calculation, what do I get? We say that age accounts for 38% of the total variation in log normal, or 38% of urea. Technically, you have to say log normal urea, right? So there are other things. So 62% is accounted for by other variables, including diet and race and maybe gender, renal functions, liver functions, and a whole lot of other functions. So in this sample, for this sample, we need to keep that in mind. In this sample, of course, there are normalized data that are available from large data sets. If you want to look at it, you can look at it as well. So I need to now calculate whether that is significant or not. So I need to know degrees of freedom. So we are looking at two variables. So n minus 1. So there is one variable. So my degree of freedom, the regression degrees of freedom is 1, right? So what I do is for my regression degrees of freedom 1, I look at my significance over here, which is now statistically significant. How do I interpret this? I interpret that there is a linear relationship. It's a statistically significant relationship between urea and age. So I say that there is a statistically significant relationship between urea and age in this sample that I have. You'll be wondering what is this 18 and 19. If you remember, the total sample size was 20. You'll recall that the total sample size was 20. So for the total degrees of freedom was 19. But for my regression, because I'm looking at variables, right? For that, it is statistically significant. Right. With this now, what can I do? Can I predict? Can I go forward? So first we calculate the 95% confidence interval. Don't worry about this equation. 95% confidence interval I calculate, and you get it on SPSS output here, right? You get 1.56 to 1.92. With this, I can look at another interval called prediction interval for log normal urea for the population, and my prediction interval is 0.97 to 2.5. Let's look at the figure for this, the actual figure for this. So this is the regression line, right? This is a larger sample now. This is the regression line. This is the 95% confidence interval for the data. And this is the 95% confidence interval for the sample that I've taken. And this dotted line, small dotted line that you see from here to here, is the 95% prediction interval for individuals in a larger population, right? So this is what I'm able to do. So now let's understand this. So the 95% confidence interval, I write it like this. For a person age 60 is 1.56 to 1.92. It is calculated separately. And the 95% prediction interval for urea is 0.97 to 2.52, right? So this is how we write it. Now, to summarize this part of our discussion, correlation, simple regression, you'll recall correlation gives us the strength of the relationship. The small r gives you the correlation coefficient, positive, negative, no correlation. We have seen all that, inverse, and all of that, right? And correlation does not equal causation. We can say that these two are correlated, right? Simple regression assesses the relationship between the independent variable and the dependent variable in interval data. And then we fit an optimal straight line. And you've seen that more than once now. And the method we follow is the least sum of squares for deviation from the line. From the mean it deviated, from the actual value, the fitted value also deviated. And then we have taken all of that, right? So that's what we have done with simple regression. So with this, let's move on to multiple regression, which is an extension of the simple regression. And this is what we do. You're going to see some equations now. I'll warn you right away. But what are we trying to do? What is our aim? We're going to predict one quantitative variable from more than one independent variable, whether they are quantitative or qualitative, categoric or continuous variables. Let's take an example of diabetes, right? You're going to hear some diabetes examples now. And maybe at this point, just after I finish this, end of this slide, I'll request Dr. Ashok or Dr. Sandeep to give us an example from psychiatry now. I want to predict HbA1c levels. I've not calculated it. This is expensive. So I have patient's age, easy, BMI, easy, duration of diabetes, easy. All this I do in the clinic. I want to predict this person's HbA1c levels. Can I do that? Right? So this is the dependent variable, right? And we're looking at the independent variables, which are now continuous variables. So how can I do this, right? So, maybe I'll stop here and request either Dr. Ashok or Dr. Sandeep to give an example to predict something in psychiatry from something that is already known.
Shall I take that, Dr. Grover, or would you like to?
Yes, sir. Please take. Yeah.
See, one common thing that you might see in psychiatry would be something like, let's say, you want to measure quality of life. Okay, quality of life is on the right-hand side of the equation, and that's your dependent variable. And we know, let's say, quality of life in patients with schizophrenia, right? And we know that there could be several factors connected with that. Let's say, but we have found on the website, I'm touching on multiple regression in a way, but let's say the age of the patient matters, age of onset of the illness matters, and we feel duration of illness matters, or number of years of being on antipsychotics matters, or we can calculate some kind of a dose or something. All these are quantitative variables, continuous scores actually. And let's say each of them has shown strong relationship with quality of life on a correlation basis. Now we are looking for regression to see, let's say in simple regression, we are taking just one score out of that and plotting the regression against the quality of life, and we are trying to see what is the relationship, and that is just exactly similar to what. Similarly, in multiple regression, but we'll be probably seeing, each of them have got independently a relationship, and we want to find out, probably Dennis will explain to you that now, about how each one of them, if they are regressed against the quality of life measure, what is the kind of strength of the relationship that is there, or how much it predicts, or what variance in the quality of life is explained by each of these variables. So how important is age in that? How important is age of onset in that? Duration of illness or dose of antipsychotics? So you're looking at each one of them, how much of variance in the quality of life is explained by each of this, though independently each one seems to have a significant relationship with quality of life, for example. Now, so each one, if you separately look for it in simple regression, like Dr. Dennis did, that will be simple regression. How much does each one of them predict the quality of life in the person? Now, in multiple regression, we've got all these factors here, and we're trying to see each one now, what percentage of the variance in quality of life is explained by each one of these variables. And he will now explain to you how we're going to do that. So, that could be, maybe you do one by one, or if the equation can kind of, he will explain that to you, how each one what percentage of variance is explained. And one of the requirements, for example, you will know, depending on age of onset and age, both will be having a relationship with duration of illness, for example, right? And duration of illness may be related to duration of number of years on antipsychotics, for example. So if each of the what you will be keeping an eye on is each one of the variable on the left-hand side is interrelated with each other. How do we go about trying to calculate the effect of each one of them on the outcome? Because then you have to make some adjustments, which we'll explain now. Okay, or if they are entirely independent. So one of the requirements for multiple regression may be that each of these variables do not have a significant relationship with each other, so that you can separately calculate the variance explained by each of them. But if they have a relationship, there could be, if they're adding on to the relationship, or if they have an interactive effect. So those kind of issues come into play. So keep that story in mind about number of different continuous variables on the left-hand side, which predicts outcome and quality of life, for example, in schizophrenia patients. And we'll keeping in mind how many of them are truly independent variables, totally independent variables on the left-hand side, and whether they have, if some of them are related to each other, do they have an interactive effect or an additive effect on the actual outcome? Keep that idea in mind. I don't know, Dennis, if this is kind of what you're going to be saying next. Yeah.
This is useful. Shall we proceed, or would Dr. Sandeep like to say something now?
No, like Dr. Ashok said, similarly, if you have assessed multiple outcome parameters in addition to, let's say, as he gave the example of quality of life, you have psychopathology assessed in the form of PANS. You have also used depression scale. Let's say you have used Calgary depression rating scale to assess depression in these patients. You have also used a disability scale to assess disability in this group of patients. So now you have disability, psychopathology, and also you have the depression in a group of patients of schizophrenia. Now, all of them are coming as significant correlation with the quality of life. But once you want to do that, which of them has the major impact on the quality of life, then that's how you'll keep on adding one by one, or you want to put everything in a single equation. That's how you'll go about. I think that will come in how we talk about the stepwise regression analysis, or the forward method or backward method. All those issues will come in as the equations are added. So I'll leave it there.
Yeah, thank you, Dr. Sandeep, for that as well. So in summary, we are trying to look at the impact of different independent factors on a dependent factor, and if we are able to predict it as well. So for example, if you're in a village setting, and you don't have HbA1c to be able to do that based on data that we have, like age, BMI, duration of diabetes, whatever, can you predict HbA1c levels? And I will show you a real live example with this we can look at. Okay, so let's move on. You're going to see equations now. You're going to see formulae now. Some I will explain very briefly. Some I will just ignore. So don't worry. Those that I ignore, if you want to dig in, remember the analogy is trying to open up the engine, right? And that's not for us. We leave it. Also, maybe I should have said this as we were starting. Some things that we keep hearing about, adjusted analysis. When I heard this for the first time during my postgraduate days, in the 90s, I was wondering, what is this adjustment? Are they manipulating data? We didn't do courses those days, unlike students these days in post-graduation, they are learning. My students are able to do logistic regression by themselves because we've trained them, we've given them the software, etc., and then they do it. In our days, we had no clue in early 1990s when I did my post-graduation. So I was very confused what is this adjusted analysis. Another thing that you will keep hearing is univariate analysis and multivariate analysis. So simple regression is univariate analysis. So single variable, you're trying to look at the impact on the dependent variable, right? Multivariate, when we put multiple figures. So once again, I'll try and show you a little bit, how these things happen, but I'll not explain too much in the interest of time, and it's not needed for us. It's good to know it, but it's not needed, right? And then we'll look at some worked examples. We'll look at numbers, and I will take time to interpret those numbers. And if you and I will show you, I'm not showing a demonstration on SPSS, so that'll take a long time. On the other hand, I will show you outputs in SPSS, and I will draw lines and show you this is what it means. Okay, so and we'll also look at clinical implications as we go along. Okay, so first is we're going to identify and define the variable, which is my dependent variable and which is my predictor variables, right? And this is the equation that we already know about. And let us say there are k number of variables. So x1, x2, x3, up to xk we have. And then the beta coefficients, and I will show you how we get that. We have k number, right? And then we create a multiple regression model from this, wherein we add, and then I will show you with a real example how we actually add it. Then we look at the residual sum of squares, right? We fit the models, right? What we do is we fit the model so that the residual sum of squares is minimum, and we use the least squares method. The principle I explained today, again, it's a revision of ANOVA that we did last week. Right. So let's take this example. As I told you, let's look at this example of HbA1c levels versus BMI. Right. With increasing BMI, what happens to HbA1c levels? So these are actual data, dots all over the place. And then we draw a regression line now. We draw a regression line now. And once again, remember, I promised you, along with the urea example, I promised to show you HbA1c and BMI. And let's look at this again. So what is happening here? Before I show you all of the animations and the arrows, what is happening here? This is the actual value, but this is my regression. And we actually have a mean somewhere here. So if you look at it, not even one, maybe not even one may actually touch the actual mean. And here, how many are touching the regression line? One, two, just two. Some of them, there's a small variation, even small variation. Some of them have a huge variation, right? So how do we account for all this? Is the least squares method. Okay, so this is the regression line. Once again, this is a quick revision. And these are the actual data. All these dots are the actual data. And this is the fitted data now, right? From here, we pulled it down and fitted it down here, right? And we pulled it down and fitted it down here, right? Do you see this? Pull down and fitted, pull down and fitted the data, right? And the difference is the residual, which is the actual minus the fitted data here. Okay, this is for all the data points. For each one, we can actually manually calculate this. Even if you have 20 different equations with the scientific calculator, we can quickly calculate this, but the computer does it for us very, very quickly. And then we calculate the beta coefficients. Now, how do we, and what do we do next? So this is the calculation of the sum of squares with the residual. Once again, this is again like a revision for you now. We have seen the squares of regression and the squares of the residual and the total squares. Quick revision again with a different example. So the same example here, regression line, and then the mean over here, and then y bar is the mean, and then yi is the actual data, right? Yi is the actual data as you see here, right? And y hat I is the fitted data. Y hat I is the fitted data for the ith patient, right? And y bar is the mean of the actual squares. So this is the equation for the sum of squares regression, and this is the equation for the sum of squares residual. SSREG regression, SSRES is for the residual, and this is the total square. So let's look at that once again. So here we have y hat here, we have this here, and this is the total, and you can relate to all of this. Okay. So once again, all of this, if somebody is just looking at this now, oh my God, this is not what I came to learn. This is all too complicated. So if we squeeze this out, what is the concept, the core principle that we have here? We have real data, right? And we are trying to predict now. We are trying to quantify and predict, right? So for that, we fitted a regression line. We fitted a regression line. How did we do that? By calculating based on the mean and based on the best fitted line for all of these data. And these are the equations for it, right? So the next step we have to do is calculating the multiple correlation coefficient R and the R square. This is the equation for it. This is the multiple correlation coefficient, right? And R, as we know, regression can range between -1 and 1. And then we have the R square as well that we take. Now moving on, let's move on to the next step over here, wherein we need to test for statistical significance of the regression model. We made the model now, right? So now this is the hypothesis in case you're interested. The null hypothesis H0 will say the regression line is horizontal. That means slope is 0, right? The alternate hypothesis, the regression line is not horizontal, and that's what we're going to prove or disprove. So the statistical test for this is the F test. You remember this from ANOVA, Fisher, right? ANOVA, and this is the calculation of the mean squares regression, right? For regression and the residual, and these are the corresponding equations. And then we also calculate the degrees of freedom, right? And finally, for the coefficient that we get, right, we use the t-test for the coefficients now. So what does all this mean? Okay, this is what it is. What does all this mean? So I now have a regression line, right? And I've calculated that for a particular level of a degree of freedom. And by the way, this is, sorry, So now you already have a preview of what is coming next, but let's go back. My mouse is very sensitive if I touch it. Okay, so here for a particular level or for a degree of freedom, is this significant or not is what I'm going to look at. Okay, all this is okay. How do I apply it? Give me a real example. Can we look at it now? Okay, so this is real data from our department a few years ago, and there are actually 50 patients. This was about 300 patient data. We took the first 50 patients to look at it. So age, gender, BMI, duration of diabetes, and HbA1c. So I'll allow you about 30 seconds to look at these data. You just focus on one of these boxes, right? So maybe 27 to 39. Look at age, BMI, and HbA1c, or look at duration and HbA1c. HbA1c is what we're interested in now, right? In this project, we calculated, or rather, we had the HbA1c. Suppose we did not have it, can we predict it? Is what we're going to look at. But now, just take a look at it. I'll leave you for 30 seconds. Just look at this data, and at the end of 30 seconds, I'm going to invite any of you to just unmute and just tell us what you think about any of the variables, either age and HbA1c, gender, not gender, leave out gender, BMI and HbA1c, or duration and HbA1c. So look at it for 30 seconds, please now. Right, so that is 30 seconds. Anybody would like to unmute and speak? We'll give people 10 seconds. If not, Dr. Ashok, please call up somebody's name. Anybody whose name comes to your mind. Just make a comment on what you between any two variables.
BMI and HbA1c are correlated, sir. As BMI increases, HbA1c increasing.
Okay, based on what are you saying that? Can you give us serial numbers?
Sir. BM 28, serial number 28, BMI 29, HbA1c is 9.1. If we see 31, BMI 24, HbA1c is 5.
Okay. Okay, those are two. Anything else?
Gender and HbA1c.
Gender and HbA1c also seem to be, there's some relationship over there. Okay, so first, of course, this is about 10 or 15 numbers that you're looking at, and to some extent we'll be able to see it. Of course, there are various ways in which we can manually do it as well. You can sort it out. You put an Excel, ascending or descending order. You can look at BMI, HbA1c, etc. Okay, so eyeballing the data at times gives us some kind of an inkling towards what is coming. I'm just taking a look at the time. It is 5:15. Dr. Ashok, I go on till 5:30 or 5:35?
Thanks, Doctor. Yeah.
Okay. Right. So I'll be in that range. Okay. Right. So here we go. This is the multiple regression equation now, right? These are each of the variables now, X variables up to K. So in our example, we are trying to predict HbA1. All right, this is the constant, right? And these are the beta coefficients. These are the different variables, right? And we get, this is the output from SPSS. So this is the constant, right? And I will show you. And this is a multiple regression equation. But before that, let's try to understand this now. Okay, so this is our unstandardized coefficients. So these are the beta coefficients. Okay. Okay, so this is our constant, right? B0, and this is B1, B2, B3, and you can have any number. So for now, we have taken 3. You can have, of course, the number of variables also matter, but you can have 5 or 7 or 8, whatever you can have, right? So this is, so our multiple regression equation will become, so HbA1c equals 1.277. Can you see this? Okay, 0.27 into age. We're now calculating only the beta coefficients, right? 2.38 here and 0.33 here. And now I can take any particular patient and include their age, BMI, and duration, and I get my HbA1c, right? And and then we leave out the significance for now. We will look at it in another item. Okay, so continuing on here, I'm just putting this together. So this is the same equation you saw there, and I'm going to add this now. So let us take patient number 28 from our model. You remember that patient number 28, whose age was 72, BMI 29, duration of diabetes 17. I want to know what the HbA1c is. Here is my equation, right? So I put this together and I get 8.175. The predicted HbA1c for this patient, based on this database that we have, is 8.175. The actual HbA1c for the patient was 9.9. So the error, this is 17% error now. If you wonder how 17 came, 9.9 minus 8.2 is 17. 17 of 99 is 17%, right? So quickly we can do the math there. I'll say that again. How did we calculate the error percent? 9.9 minus 8.2 is 17. 17 of 99, 17 of 100 in a way is a 17% error. So with this data, I was able to get 8.2 instead of 9.9. There is a level of error, right? But of course, if you have a larger sample, which is a little more normally distributed, etc., we can improve on the precision of our prediction. But using this, we were able to predict. So this is what I wanted to tell you. So once again, let me explain that equation to you. So we are trying to find out HbA1c, right? This is our constant, right? And this is B1, B2, and B3 for age, for BMI, and the duration. And I get this 8.175. I'm able to predict now my HbA1c. Dr. Sandeep briefly mentioned the order of entry of the variables. This is important, and I will allude to it a little later as well, but I'll run through this quickly, right? So there's something called hierarchical entry based on some logic. I decide this a priori based on some logic, based on past research and data available. I will say this variable has to go first, this variable has to go second, this variable has to go third, right? I can either put the variables one by one, or I can bunch up variables and put it into the model. All of these we can do, right? So for example, if BMI is a known predictor of HbA1c from past research, age and duration of diabetes are unknown predictors. So what I would do is I'd enter BMI first, followed by age and duration of diabetes. These are all contentious issues. I mean, this is what I'm telling is right, and people do follow it. But these are always contentious issues, and people go back and forth. But let me tell you first the order of variables, and then we will discuss the contentious issues. So other types of entry are the forward entry method, the backward entry method, the stepwise entry method, and the simultaneous entry method. I will make a case for the simultaneous entry method in large databases or large data studies, and where that is more conservative, and big journals actually accept the simultaneous method. Right. So let's I'm going to skip this. This has got a lot of detail on forward method, the first predictors, when do you add the first predictor, second predictor, etc., and the stepwise method, the backward method, and all of that. So I will end multiple linear regression with this example of fasting insulin levels and metabolic risk factors in type 2 diabetes patients. Right. So this was done in Japan and published about 10 years ago. The objective was to investigate the relationship between fasting insulin and metabolic risk factors in type 2 diabetes patients, about 4,800 patients. Let me go here. And multiple linear regression analysis was used, wherein the dependent variable was fasting insulin, and various clinical explanatory variables were assessed. So, okay, so what were these? This is statistical analysis. One of you all did mention, I think, this is a part where in the journals we usually skip. So I deliberately cut and pasted actually there and explain it for you as much as possible. So these were all the variables: sex, age, BMI, waist circumference, blood pressure, HbA1c, fasting insulin, triglyceride, LDL cholesterol, HDL, microalbuminuria, were done for 10 years, 2000 to 2009, using a one-way ANOVA. And then what they did is multiple linear regression, right, to analyze what were independently associated with this fasting insulin levels. Okay, so two results I'll give you, one graph and one table, right? So over time,
Yeah.
fasting insulin.
Dr. Dennis, sorry to interrupt. Yeah, there was one question which is probably very relevant at this instant. If you can mention that in the previous slide that you mentioned the independent variables that were independently associated with the outcome variable of interest. There's a question that says if we want to predict on the dependent variables, do we use only those variables which are significantly associated with the independent variable? So I think it's kind of exactly with this. So I thought I'll just cue you off.
No, thank you for that, Dr. Ashok. Simple answer is yes, right? So when we add it in the model, right? Actually, okay, this is where you work with your statistician now. Okay, so one is okay. If at all you're making notes, this is something that you need to write. So firstly, during the design of the study, remember I said this is how we work with statisticians, and you'll remember that little cartoon, and please don't forget that one. That's really, really important. So during the design state itself, you discuss with the statistician. Of course, you have clinical knowledge, right? And you will want to add as many variables as possible. But there as well, please be cautious to only include those variables. Remember, collecting any variable is expensive. It costs money, right? Oh no, do this test, we'll see later. No, it should be clinically meaningful as well. In addition, some of them which you don't know, you could say, I'm not sure, but let me collect it. But don't overdo the second part. So that is during the design stage. Next, once the statistician runs the univariate analysis, he or she will show you the first. I mean, that's how to work with the statistician. Can I look at the univariate analysis and show me all the variables that are significant here, right? Okay. Then the next question you work with is clearly, without a doubt, as Dr. Ashok mentioned, and probably that's the question. I'm not seeing the chat box here. Is which variables do I add in the model? Simple answer is only those that are significant. Now you can work with the statistician and take liberties and say, no, something that is 0.053 also I will include, 0.061 also I'll include, but you must have a rationale for that. And this is where you have a little discussion argument with the statistician, right? So simple answer is only those that are significant you add in the model, right? And then you look at what happens with it. I'll show you an example, I think, after this. Once we do multiple logistic regression, I think that comes in. Okay, so we've done this. So with age or over time, fasting insulin is coming down. Over 10 years, is the fasting insulin coming down, and over time, you see BMI going up in both men and women, right? Now, so this table, let's look at a little carefully. Okay, so this is the key table from this analysis, the multiple regression model for clinical background factors, right? And fasting insulin levels. Now below, regression table, they'll actually give you an elaborate discussion. Elaborate, description of what is model 1, what is model 2. And of course, we have to write that very carefully and put that underneath, because along with the numbers, we'll have to verify what is what. Okay, so give me 1 second. Okay, so the dependent variable was fasting insulin, and independent variables were your LDL cholesterol, HDL, triglycerides, microalbuminuria, waist circumference, BMI, right? So waist circumference was included in the model 1, and BMI was added to model 2, right? The R values they have given you here, and data were adjusted for sex, age, HbA1c. Adjusted means these factors have already been accounted for in the analysis, and this is what we get, right? So this is model 1, and these are the beta coefficients. So with increase or decrease in something, if the parameter that we're looking at is going in the same direction, it will be positive. If it's going in the opposite direction, it will be negative. First thing to keep in mind, right? And is this significant or not is given by the p-value, right? With time, what is happening to insulin values, right? It is going down. Waist circumference going up. BMI is looked at in the next model, right? Waist circumference is going up, significant. HDL going down. Going down by how much is also quantified here, right? And LDL is not significant. I mean, I don't like this people writing not significant, and I personally would prefer, giving the actual p-values. But here the p-values are really small. But don't tell us not significant. We can figure out. Give the actual p-value. So this is not a good way of writing it. Right? This is not applicable because this is not a model for BMI. It is a model for waist circumference. And this is model 2 similarly. So what is the conclusion here? Let's skip this and go to the conclusion. During 10 years, the decreasing trend in fasting insulin was related to increase in waist circumference and BMI. Right? So this is how they give it and the way we interpret it. And we have to read the discussion part carefully as to how they've interpreted not just the positive and negatives, right, but also the quantities. Look at this. I mean, between this and this, there's a 10 times difference between these numbers. There's a 0 over here. So we need to look at it carefully. Okay, with this, let's move on to logistic regression, with which I will conclude. Both we will do simple logistic and multiple logistic regression. Dr. Ashok, I think I will take another 5 to maybe 10 minutes from here. Okay, let's go back to the same example, right? Now, there we saw actual HbA1c, right? But here now, for the purpose of this example, we are categorizing HbA1c into good control, less than or equal to 7, and we're coding it as 0, and poor control, greater than 7, coded as 1. Now, the dependent variable has become dichotomous. So, in other conditions, this could be mortality, dead, not dead, or dead or alive, with an MI or no MI, schizophrenia, relapse or not, successful suicide attempt or not, or attempted or not attempted, successful versus non-successful. I hope these examples in psychiatry make sense to you. So one other thing, really, although I'm giving you this example, please keep in mind, anything that's a continuous variable, please write this down. Anything that is a continuous variable, do not categorize them. We lose power in the analysis. Statisticians will go mad when you do this. Okay, but we tend to do that. We collect age and then we say, adults, okay, 18 to 25, and then 26 to 35, 36 to 50. No, don't do that. Put age as such. Right? If you have any other continuous, and I'm sure Dr. Sandeep is going to tell us this, right? So do not categorize continuous variables. Although intuitively in our mind, we like to do that. But for the purpose of this example, I have done it because I'm using the same data to show it to you. Now, it is categorized into whether there is good control or poor control of diabetes. So the research question now is BMI a predictor of poor diabetes control, or can BMI predict diabetes control? That's another way. We can leave it open. So we are also going to look at covariates, age, gender, and duration of diabetes, and you'll see that nicely, and other confounding variables as well we can include in the model. So now what has happened? Exact same data, but this is HbA1c levels, and I've now categorized that into 0 for good control, right, and 1 for poor control. So that's what I'm going to put in my data there, and to analyze it in which software we're going to use. Right, so that's the same full data set. Okay, so value of 0 or 1. So what happens now? There are no dots all over the place. This is 1. All these are poor control, and all this is good control. Right. So now, as you see, there is no linear form here. So our assumption for linear regression, you'll remember that from about 30 minutes ago that we did. We need to have a linear relationship with the independent variable. So I cannot do multiple linear regression. It's not appropriate. So therefore, what I'm going to do is I'm going to transform it, right? And I'm going to work with the transformed values. What transformation I'm doing? I'm doing logistic transformation, and that's why this is called logistic regression. And this is a parametric regression approach that we'll do. Okay, same. What are the steps in logistic regression now? Right, I'm defining my variables. Defining my variables. HbA1c is the dependent variable. BMI is the independent variable. Okay, and this is the relationship I'm looking at. This is my research question. All these are my confounders. These are my independent variables, right? This is the equation we can write. Then I'm going to do logistic transformation, right? And so I'll skip all of this and I'll come down, right, to this equation, right? If I do one variable, right, it's called simple logistic regression. If I add the confounders, it's called multiple logistic regression. So we'll just focus only on this part now. Okay. So if I'm doing only one variable, right, control, no control, right, it's simple logistic regression. If I'm going to include all the confounders, it's a multiple logistic regression, right? So now we have to fit it. Once we draw a model, we have to fit it. And a few sessions earlier, we briefly looked at maximal likelihood estimation. And I said we will look at it when we do regression analysis. So this is the method to fit for logistic regression, the MLE method, or the maximal likelihood estimation approach. And then we select coefficients that make observations most likely to have occurred. Which is closer? So now we don't have a line going across and dots all over, right? Which one is closer to that side? Which one is closer to this side? We are going to fit it. That is the principle behind the maximum likelihood estimation, right? And then what we do is calculate the log likelihood, and I'll skip that part. And then we have a predictor included, and then we're going to look at the difference between the two log likelihoods and multiply that by 2. And this data that we get follows a chi-square distribution. By now, you're familiar with different types of distribution. We looked at the T distribution. We use it for T-test. We looked at the F distribution, of the F statistic that applies to ANOVA. Here, because this is not parametric. Remember a moment ago, I told you this is a parametric test. So this follows a chi-square distribution. And this is the chi-square. This is how we get the model fit, as we would say, right? The new log likelihood minus the baseline log likelihood is this is where we get the chi-square, and this is the degrees of freedom for the numbers of variables that we have. What are we trying to do? We're now trying to see, we are trying to now calculate and quantify the variability, and we'll get a ratio. Those are the next thing. So we're going to assess the model. We calculate R square. You will see this in journals, the Hosmer or Lemeshov's R square, or Cox or Snell's R square. These are different, and these are whole new sessions, and we'll leave on that, right? Then we assess the contribution of the predictors, right? We use the Wald statistic, which is similar to the T statistic. Now that we're doing regression, now it is a parametric test now, right? Then we do a T test over here. Finally, we calculate the odds ratio. If you missed out everything so far, don't worry. We reach the odds ratio, and I'm going to spend some time explaining to you how the odds ratio gets in and how we interpret it, right? The odds ratio is the exponential function of the beta coefficient, or the B coefficients, right? And I will show that. I'll show the in the next slide. You're going to see the SPSS output, and what do we take from there? We'll take. So here is the simple logistic regression. What is our goal now? To predict diabetes control from BMI values that I have in a data set, right? So here is my BMI, and here is the constant, right? This is my beta coefficient, and this is my 95% confidence interval, the upper and the lower bound. Since we have two variables, the degrees of freedom we use is 1 over here. So what do? We have the odds ratio of 1.42. Here is my 1.42, right? 1.42, and the 95% confidence interval is here, right? And this is the p-value here, right? The exact p-value there. So what is my conclusion? BMI significantly predicts HbA1c control. Significantly predicts HbA1c control. So this is statistically significant, highly statistically significant. But can I interpret this odds ratio, right? How do I interpret this? This is important. Please listen carefully. With unit increase in BMI, there is a 42% increased chance of having a poor control of diabetes. From this data set, this is what we're going to tell. So what are the clinical implications? You're sitting in your clinic, and after let's say 6 months, a patient comes in. Last time the BMI was 28, and this time it is 29. So you say there is approximately a 40% increased chance that this person's HbA1c is crossed 7. I don't have to send it, right? I don't have to spend those few hundreds of rupees for that patient to figure out what the HbA1c. Based on these data, I know it, and I can predict it, right? So we also look at the goodness of fit over here. So what is the meaning of goodness of fit, right? Is this model good enough? In simple terms, is this model good enough? And we get this from our there's something called an omnibus test. Multiple tests are done, and then we take the test for the model, right? I get a chi-square value here. Remember, this is a non-parametric test. Chi-square value for this degree of freedom, it is significant. So this is how I write. So along with a simple logistic regression, we can or it's good to write the goodness of fit as well. So this is the chi-square 11.55 at a degree of freedom equals 1, and this is my p-value equals 0.001, right? So this is what we got, right? So let's look at this table now. Predictor of poor, HbA1c, right? BMI here, right? And the variables added in the model, right? For BMI, I get an odds ratio of 1.42, right? Next column is adjusted odds ratio. This is only for BMI, so it's not applicable. And this is the confidence interval we've seen, and this is the p-value you've seen. When I add age to it, this is my adjusted odds ratio, right? The odds ratio changes just about marginally, still statistically significant. I add duration of diabetes in the model, 1.43, no change, I would say. I add gender into the model. Remember, this is categoric now, no change, right? Statistically significant. So in other words, other variables did not significantly predict the outcome. That means what? Oh my God, BMI is so damn important. It is not being affected by age. So whether you are 35 or 65, if your BMI is bad, your diabetes is not going to be under control. I'll say this again: duration of diabetes, right? Age, whether you're male or female, does not matter, right? Your BMI, irrespective of age or how long you had diabetes, BMI predicts your, from these data we have, right? BMI predicts your HbA1c levels, whether it's under control or not, right? So this is the interpretation of BMI significantly predicts diabetes control even after adjusting for other covariates. It did not change here. But I'm going to show you another example from a project that I did. I think you're familiar with it. I've shown it before as to how when we add variables, it changes. So how do you further interpret it? With 1 unit increase in BMI, there's a 42% increased chance of HbA1c being not under control. This is what it means. So let me give you, I think I've shared this with you when I did registries. So this is the treatment and outcome of acute coronary syndromes in India. The CREATE study, which we did and published in the Lancet in 2008. This is led from St. John's. And so, okay, let's skip all of this. So let me explain the statistics here. This is descriptive statistics. Let's go here, okay? To assess the association between socioeconomic strata and mortality from acute coronary syndrome, we did multivariable logistic regression in which the dependent variable was mortality at 30 days. Independent variables were so many risk factors, okay, sex, age, smoking, etc., clinical features, okay, at presentation, blood pressure, heart rate, BMI, kilo class, and socioeconomic strata, right? To assess the effect of different treatments, we did another multivariate logistic regression to establish whether any association between socioeconomic strata and death could be explained in differences in treatments, right? The additional independent variables in this analysis were type of the hospital they went to, time to get to hospital from symptoms, the kind of treatments they got, right? Key treatments, right? Interventions included. For these analysis, we used forced simultaneous entry, not hierarchical, not forward, not backward, nothing. Used forced simultaneous entry rather than stepwise selection. See, automated stepwise, automated stepwise, your computer will give you have to tick what option you want. So the best is for simultaneous entry, particularly when you have so many different variables. See, so many different really important variables I'm looking at, right? So, right, stepwise selection, you know, and I'm sure you've heard this, right? You know, you go to a statistician and dump data. And if you give them lots of data, the statistician can turn around and ask you tell me what results you want, I'll give you. These are the ways in which statisticians can manipulate data, right? Manipulate in the sense, maneuver data, let's say, not manipulate. Sorry, that's a wrong word here. We're talking about good statisticians, not bad or conceited statisticians, right? So with these different maneuvering, you can alter to some extent, particularly when you have large data. And you'll recall CREATE, we had about 21,000 patients and a lot of data. So we use the forced simultaneous entry, right, which is conservative, and there are no discussions about it. Okay, so about 21,000 patients, and that's what we did. We categorized them into rich, upper middle class, low middle class, poor. This is treatment and variations by socioeconomic strata. And you will look, and you will see quickly, I'll not go through all of these numbers, except for antiplatelet, all treatments compared between the rich and the poor was highly statistically significantly different. Let's take just a few examples. Thrombolysis 61% here, poor 52%. Let's take lipid lowering 60% here, 36% here. Let's take angio 41% here, 8.6% here. PCI 15% here and 2% here among the poor. So, and there's a nice gradient going right across like this if you see, right? So this is a variation in treatment. What was the impact on mortality? So this is the crude death rates. In the rich at 1 month, 5.5 died, upper middle class 5.9, 6.5 and 8.2. I've explained this to you all earlier. Let's assume this is 8 and this is 5. How is this so highly statistically significant? 8 minus 5 is 3. 3 out of 5 is 60%. So this is 60% higher mortality. The numbers look small and sometimes we ignore it, right? 60% higher mortality compared to the rich. That's why you have such a high statistically significant difference. So now I'm adjusting for risk factors, and these are my odds ratios, right? So we fix the odds ratios in the rich as 1. Compared to that in the upper middle class, 16% more, lower middle class 32% more, and poor, here is a 60%. It still remains. So even if I adjust for risk factors, this significance still remain, and although the level of significance reduced a bit, but it's still highly statistically significant. We still write it as equal to 0.001 right here. So adjusting for risk factors did not make much of a difference. But when I adjusted for risk factors and treatments, just follow my marker here. These are the factors that I put into the model: treatment, type of hospital, time to hospital, drugs and interventions. You see what happens to the odds ratio: 1, 1, 1, 1, and the p-value is also 1. So when we remove, so this is the interpretation of this. When we remove the variation in the treatments in these 4 different groups, the difference in mortality disappeared. So can you see this is more or less 7 everywhere? 7, 7, 6.5, 6.7. So this is the adjusted rates, and these are the odds ratios. So what is the clinical implication of this? If poor people got the same treatment as the rich people when they came to hospital, we can save, we can save 60% or here 60% of their lives at 1 month. These are massive implications. Okay, so let's summarize, dear friends. Multiple linear regression and multiple logistic regression. So fitting a linear model, least squares method is linear regression. Significant test is the F test for ANOVA, for the coefficient is T test, and this is the equation that we draw. And then we can look at the proportion of variance and explain the predictors, right, by this multiple regression equation. Similarly, what method do we follow for logistic regression? Log transforming data to fit it, and we use the maximal likelihood approach. As I just told you, the significance test is the model chi-square statistic, and we use the Waltz test for it, and the result is expressed as an odds ratio with confidence intervals and p-values. So just a quick thought on sample size, and I will summarize the overall session. Very, very simple. For multiple linear and logistic regression, for every predictor variable, the sample size should be at least 10. So if you have 10 predictor variables you're looking at, minimum you need 100, right? Minimum you need 100. So if there are 4 predictors, you need 40 samples, but I'm sure we are interested in many more predictors. So that's a rule of thumb, but please work with your statistician to look at this. Okay, so let us summarize the overall session. Sorry, I took a little longer than what I planned. Right, okay. So to measure relationship between 2 variables, we just do a simple correlation, right? And we calculate the R values, and then the correlation, +1 or -1. The closer it is +1 or -1, stronger is the correlation. We know this. To predict one variable from the other, we do regression, right? That's what we discussed today. The dependent variables are assessed, and if they are continuous, we do linear regression. If they are dichotomous or categoric, we use logistic regression. And depending on the number of independent variables, right? If there is 1, I do simple linear regression. If there is more than 1, I do multiple linear regression. Similarly, for logistic regression, if there is 1, I do simple logistic regression. And if it's more than 1, we do multiple logistic regression. In essence, what we're trying to do is looking at the relationship and quantifying the dependent and the independent variables. And they have huge implications, as you can see here. When I'm sometimes interested only in one variable making a difference to the other, but we have a whole lot of other variables that come in, and all that we know from our clinical knowledge as well as from previous research, we'll have to include it, account for it, look at the confounders and explain it, quantify it and explain it. So I will stop with this, and happy to take any questions, or we could do it even towards the end after Dr. Sandeep.
Thanks, Dr. Dennis. Yeah, we'll take more questions towards the end after Dr. Grover's presentation. Just two quick questions which may be connected with what you spoke, Dr. Dennis. Is modeling decided prior to design of study or during analysis phase? Is one.
Okay, ideally while we are designing the study itself. Okay, that being said, the latest we can do it is when we are writing the SAP. The SAP is a statistical analysis plan, right? And when is the statistical analysis plan done? Somewhere halfway while we are collecting the data set. See, initially we are, ideally you can write statistical analysis plan even before, along with the protocol, but in an ideal situation, but things are not really ideal. Get the protocol done, get it approved, we start recruiting, collecting data. And as I tell my colleagues, okay, now data collection is going on cruise control, let's write the statistical analysis plan. And I have seen SAP documents which are 150 pages long, and it's written by a statistician, right? And all the models are written there. The way, I'm fast tracking. So first we write the descriptive and the univariate analysis, and coming to regression, we write the type of models, the way we're going to enter the data, and also even before that, the way we quantify this data and any transformation, all of that is written in.
Yeah, you're right now frozen, Dr. Dennis. I think just give it 10 seconds more. If you can't come back, we will proceed. Yeah. While we wait for Dr. Dennis and see if he can come back immediately, it's a great pleasure to have Professor Sandeep Grover with us today. Dr. Dennis, are you back?
Yeah, sorry, he's just crashed and I'm just back. Okay, so I was just telling you, and this is the last part. So all of the variables and the way we're going to quantify it, what models are we going to use, all of that is written. Actually, a whole lot of equations and dummy tables and all of that's what a statistical analysis plan is. So we do that before we even do mean and medians for age and whatever else, right? So before, in a trial, this is actually submitted to authorities, and what we say is kind of approved. It's written by statisticians along with the principal investigator, and we all sign off on it, and then we start the analysis. I'll stop there with that.
There are more questions. Some of them are follow-up questions. We'll come to that after we have completed Dr. Grover's presentation. Great pleasure to have you with us. As you all the participants here know, Dr. Grover helped us in understanding case control analysis in psychiatry as well as cohort studies in psychiatry. And at short notice, he's kindly agreed to be part of this today's presentation as well. Professor Sandeep Grover, Professor of Psychiatry at PGI Chandigarh, now has become, we are all very acquainted with him from the last two sessions. Apart from the fact that he's involved with many studies and he's got several grants going, I would just like to insist that probably in this side of in this century, from Indian psychiatrists, he probably has the largest number of publications that is going by how frequently I see publications from him and pick up. So it's a great pleasure learning from you, Dr. Sandeep. Thanks for being with us. Over to you.
Are my slides visible?
Yeah, visible.
Yeah, and am I audible? Yeah. Good evening, everyone, and I would like to thank Dr. Ashok and Dr. Dinesh for including me in this workshop. In today's presentation, I just would like to briefly or maybe go into much more basics about what we do in psychiatric research. And we have done about the analysis part and everything. But once it comes to selecting the questionnaires and everything, or how we interpret the data in terms of whatever data we collect, I'll start from there, from the basics, and then go into how we go on to select the different questionnaires and the different scales. So it may sound very simple to start with, but I think that is required, and that's why I have tried to design the presentation in that way. So what are the usefulness of rating measures? So if we just try to understand what are the different rating measures, these are the core to any kind of the quantitative research in psychiatry, and they aid in a so-called discipline dialogue between the clinicians or the researcher, and these are equivalent to any kind of investigation report in field of medicine. For example, when we talk about hemoglobin levels or HbA1c levels, we were talking about. Similarly, if we talk about that HbA1c is deranged, but similarly we talk about the depression is severe or mild or moderate, that is determined more or less by the rating scales. So what are the different rating measures? These are precisely defined format which focuses on the conversation between the respondent, that is the patient or whoever is the participant in the study, and the questionnaire on a relevant area. And all respondents will be given the same kind of questionnaire, and they are invited to communicate in the same shared language with a specified option choices. Means, for example, all of us are sitting here and all of us are supposed to rate this session. So we all will be given the same question, and we have to rate our satisfaction with the sessions, let's say from 0 to 5. So that is where we need to understand, that is how we go about the rating measures or the rating scales. So rating scales are, again, we need to understand, are usually the close-ended measures with more than one response option, or more simpler to understand from our MBBS days of 10+2 days of preparing for the entrance examination. These are like MCQs, that you are given a question and you are supposed to choose one of the given options. This is in contrast to the qualitative study, where you will have more of a open-ended questions and you are free to respond where you want to, and the researcher is later on going to determine the theme from there. So that is where the difference lies in. And the rating scales seek respondents' feedback in a comparative form for a particular issue. When we say comparative form, is you have to choose one of the options, and that will help us in collecting the data or collecting the information in a qualitative way or the quantitative attributes of that particular issue. Where when I talk about qualitative or quantitative here, we need to understand that qualitative means how you feel about something, or how much is the intensity of something. So again, I'll discuss this maybe slightly later. So the rating scales usually improve the collection, synthesis, and the reporting of the information, and they ensure complete coverage of the relevant issues which we are trying to assess. For example, we want to assess depression. As a clinician, you can say it is mild, moderate, severe. But if you have not used a rating scale, how would you rate the severity? You don't know. If you just did a clinical assessment. So, or if you have done a clinical assessment, if you are saying the depression is severe enough, on what measures you're talking about? Maybe you're calculating the ICD-10 criteria. But for each item, or let's say each criteria, what is the severity? That you may not be able to judge just by a clinical interview, or if you're trying to communicate with anybody, you need to again explain that. But if you're talking using a rating scale and you're saying is getting a score of 3 on PHQ sleep item, everybody knows what we are talking about. So this helps in categorization and the quantifying the data, and also rating scales help us in carrying out a rapid assessment of a specific construct, and also help us to get a numerical score which can be readily interpreted. And the important thing, the rating scales, depending on the kind of study which you want to conduct, can be completed by the clinicians, the patients, or the significant others. The clinicians here, when I talk about the rating scales, here basically it may include something like the clinical interviews, where the clinicians themselves are interviewing the patient, and based on their judgment, they are then making a judgment about what is the score to be given to the assessment of a particular issue evaluated there. So as I've said, that it helps in communication with the colleagues, also with the patients, or maybe the caregivers once you want to communicate what is the severity, what is, and it also helps in making a clinical decision. For example, you want to use ECT or not. So ECT, one of the indication is severe depression. So if the patient has severe depression, you're thinking of giving ECT to the patient. So from that perspective, if you've used the rating scale, you have used HDRS, and HDRS score is about 40. You can very well say that his HDRS score was 40, and that's why I consider using ECT. So it helps you make a clinical decision. And it also helps in screening and monitoring a patient. For example, if you want to evaluate a patient whether he has or does not have a depression. For example, a patient is supposed to be started on interferons, and you are asked by your hepatology colleague that tell me this patient has depression or not. So you use your PHQ to screen the patient to assess whether he has depression or not. And maybe the PHQ is again applied at 2 weeks, 4 weeks, 6 weeks to see what is happening to the patient's depression score. So it also helps to monitor the progress, and by that you can say that with interferon did he develop depression or not. And these are cost-effective measures because these scales do not require that much of time when we compare that to a longer clinical interviews or maybe the manpower which is required to carry out the structured assessments. The rating scales, again, we need to understand there are two broad things which when we look at ratings, what are the different types of scales and what are the different categories of scales. So let's try to understand the different types of scales. These are basically how the scales are formulated or how the items are generated. So when we talk about the type of rating scales, so we have the numeric rating scale, the verbal rating scale, the visual analog scale, the Likert scale, the graphic rating scales, or the descriptive rating scale. In psychiatry, most of us end up using either the Likert scale or the descriptive rating scales. Other scales are also used, but most of the you'll see that psychiatric scales which we use are either the Likert scale or the descriptive rating scale. Let's try to understand what are these. The numeric rating scales are basically, these are scales which you just use numbers. For example, this is where you want to assess something like how much was the itching the patient was having. So at one side there is no itching, and the other side the worst imaginable itching is there. That's what the option you have given to the patient to choose one of them. So that is where the patient is going to choose one of the options based on the number which he thinks will be able to describe his level of distress or the experience with the itch. Whereas the verbal reporting scales, these scales have they will compile a number statement that describes the intensity. Let's look at this. That here when we talk about that there is some description, there is no pain, mild pain, moderate pain, severe pain, very severe pain, and the worst possible pain. So these are verbal rating scales where the person will choose one of these options rather than choosing a number on 0 to 10. And when it comes to the visual analog scale, again, visual analog scale will not have the so-called numbers in between. There are just two endpoints. Then the person is allowed to choose any of these. So here the rating is again can be, let's say 0 to 100, so that you can choose 55, 56, 57, 58, or here if it is 0 to 10, somebody can choose 5.5, 5.4, 5.3 also, in contrast to a numeric scale where you have to choose one of the absolute numbers. So that is the basic difference between the visual analog scale and the numeric scale. Then are the Likert scales. Here, these are the commonly used scales in our psychiatric practice that they assume that the strength or the intensity is linear. So when we say this, that whatever the options you are giving to the patient, they are in a continuum and the patient chooses one of those options. And usually in psychiatry, what we choose is like whenever we give options to the patients in different scales in terms of how much they agree with that, or what is the frequency, or what is the importance, the quality, the likelihood, and so forth. For example, in the agreement, you give a statement to the patient, ask them how much do you agree. For example, how was your mood in last 2 weeks, or your mood was very bad in last 2 weeks. So somebody will say strongly agree, strongly disagree. So depending on that, you will determine that what kind of score you want to give to the patient's response. So similarly, the frequency, or that if somebody is having pain or let's say sleep disturbance, how frequently you were having sleep disturbance in the last 1 week. So somebody can choose one of these options. So from that point of view, the Likert scales are the most commonly used scales in psychiatry. Then are these graphic rating scales. These are mainly used in the pain measurement, and here the graphics are combined with the assessment, so that rather than patient being just given the numbers, you give the patient the options to choose one of the facial expression or the whatever graphics you can, or the smileys which you can choose to determine the expression of their experience. Then there are the descriptive rating scales, which I said are the second most common type of scales which are used in psychiatry. That these contains a thorough explanation for the purpose of gathering information with deep insight. So again here, for example, if you're trying to assess the depressed mood, you're defining, you're giving a score 0, 1, 2, 3, 4. Here again, we are thinking that there is an order in this, and there's a so-called anchor point or the descriptor which is there, on the basis of what these are two descriptors from the HDRS that you rate based on all this assessment, that how are you going to rate the patient's sadness. So based on this, again, you need to understand that these descriptors are not mutually exclusive, and many times people combine. For example, the numerical rating can be combined with the graphical representation also, or the numerical rating can be combined with the verbal numbers also. So that is where you need to understand that whatever scales which you are using, the responses which you are trying to use for the scale, that's very, very important for you to have an idea about when you are choosing your scales. With this background of the types of scales, let's come to the categories of the scales. So for category, we all have gone through the statistics by this time in this whole course. We know quantitative data and the qualitative data and what are the discrete continuous variables. I'm not going into it, but gradually it will unfold what I just want to convey to you. So rating scales again can be divided into four broad categories, that is the nominal, ordinal, interval, and ratio. And when we say this is an order that how the scales are. The nominal scales are the simpler ones, which will not give you actually the scores, but just the categories. When we talk about the categorical variables, the ordinal scales have an order in that. The interval will also have an order, plus there is so-called, you can assess the intervals between the variables, and the ratio additionally will have that it can accommodate a value of 0. So that's where you need to understand, and this is the increment, how these go on. So the nominal scales are simple, like when you collect the data for your socio-demographic, the gender, or let's say if you want to categorize the marital status, these are nominal scales where you are collecting the variables as the names, so-called male or female, or married or unmarried, and there is no specific order between the two options which you have for the scales. For example, what is your hair color? Again, there is no particular order in this hair color from that perspective. Whereas in ordinal scales, that is definitely there is a rank or order in the data, although we actually do not establish the same, but there's some degree of variation between these. And so, for example, when we talk about how satisfied you are with your life, so totally satisfied, satisfied, neutral, dissatisfied, totally dissatisfied. So here, if you look at that, there is some order to this when we are trying to evaluate the satisfaction level. And most of the scales have this kind of are the ordinal scales. Now comes the interval scale, because this is something confusing between the ordinal scales and the interval scales. The interval scales, in addition to the labels, the orders will also have a specific interval between each of its variable options. So in interval scales, there's an order. The difference between the two variables is meaningful and equal. For example, 70.1 and 70.2. You know that there's an equal difference the two, and there's a presence. If at all there's a 0, it is an arbitrary number which is determined here. So, and the interval scales hold no true 0 when they are trying to represent the scales. Again, if you're talking about here, the commonly used example in literature is the temperature, there where we talk about 0, but there is no absolute 0 in that sense. That's what the literature suggests. And the ratio scales are considered to be the ultimate goal or the ultimate level of scales, which when it comes to data measurements. And they can also accommodate the value of 0 on any of its variable. And the ratio scales will tell you the exact values between the units, and they also have an absolute 0. And here, these variables can be meaningfully added. So the ratio which you collect can be added, subtracted, multiplied, or divided from each other. So ratio variables never fall below. In contrast to that, the interval variables can fall below 0 also. And sometimes people, just when they're trying to make the Likert scales, there also the so-called the order scales, they at times have both positive and negative. So you need to remember that. So height and weight measures from 0 and above, but never fall below 0. So you can have it range starting from 0 to above, and you cannot have less than that. And the so-called the categories which will come on is that there are comparison from one to other. And for example, how much time do you spend daily watching television? It cannot be -2. So the temperature can go minus 20 degrees, but that the watching time of television cannot go to the minus hours. That's how it is conceptualized as the ratio scales. Now, this becomes important when you're trying to use the statistics and also understand how you're going to evaluate your data. So remember that the true zero is only there in the ratio scales, and other scales do not have a true zero. And there's an order to this, that the nominal, ordinal, interval, and the ratio scale. So as one keeps on going up, the kind of data analysis will change. And here it comes very, very important that the mean is usually calculated for scales which are based on interval and the ratio. So this is very important to understand, but many people do end up using mean also for the ordinal scales. We unknowingly, we also don't understand it, and we keep on using it in our analysis. Many times you escape the reviewer's comment or reviewer's observations on this, but ideally only the interval scales and the ratio scales for which you should be calculating the mean. So that is one thing which we need to remember. For ordinal scales, usually the mean is not advisable, and you calculate the median and the mode. Now comes, with this background of the scales, let's try to understand the selection of the rating scales. Now, again, here, for example, I'll start with the example of that there are multiple scales for assessment of depression. And for example, if you look at the scales I've listed here, at least I've listed about 7 to 8 to 9 scales here. Now, which depression scale are you going to select for your study group? How are you going to determine that? If anybody wants to unmute and say that. Yeah, anybody wants to take up that question?
Sir, if I may answer, sir.
Yeah, sure. Please go ahead.
Yeah. This patient health questionnaire, I'll do it in a large sample where on a we are doing a screening kind of thing on a health camp like that. And Hamilton depression rating scale will be for a smaller sample in hospital based like that. So we'll choose on that basis.
Okay, fine. Thank you. We will come to this. Yeah. Now, so the factors which will determine the selection of the scale is the purpose. As one of your colleagues said, that if you just want to screen people in a camp kind of a situation, you may use PHQ. But if you want to use something to make a proper diagnosis, maybe PHQ may still have its advantages and disadvantages. And if you want to do severity rating along with the diagnosis, again, then you will have to determine which scale you want to choose and who is going to complete. Is it the clinician? Is it the patient? Is it the caregiver who is going to choose the scale, complete the scale? That will again determine which scale which you are going to select. And similarly, if your study group has only primary depression without any comorbidity, or somebody has comorbid medical illness, that will again determine selection of the scale. And the other issues which comes in are the feasibility issues, like whether the scale is copyrighted or not. If the copyrighted scale is there, still you can write to the author, seek permission and use it. Maybe you may be lucky not to pay anything for that. Many people allowed you to use those scales. And there are other scales which are copyrighted, but maybe paid scales. So again, you need to have that idea when you're selecting your scale, because otherwise at the time of publication, again, you may have a problem. Somebody can raise the copyright issue. So it's always better to check the copyright issues for the scales. Usually for the non-funded studies and for funded studies, again, there are people, those who hold copyright have different policies. If it's a non-funded study, they will usually allow you to use the scale. But if it's a funded study, again, they will ask for some amount of money to be paid to use the scale. And again, some people will ask a particular amount of money to be paid for the whole project. Some people will ask money for each use of the scale. So again, you need to understand these factors when you're choosing your scale, or when you're writing your grant also, you need to take these factors also into consideration while you're choosing which scale we are going to use, because that will also affect the amount which you're going to spend on the instruments. So that is where you need to have some awareness about this. Then again, age may become an important factor in selecting the scale. For example, your study group is children or the adolescent or the elderly. So accordingly, you will decide which scale to choose. So these are the different factors which also must be taken into account when you're choosing a scale. Now, the factors, again, the other factors which determine the selection of the scale include the psychometric properties, that is the so-called the reliability and the validity of the scale. So we need to understand what are these. I'll be discussing this in the later part of the presentation. Then the other psychometric properties like sensitivity and specificity, and the positive predictive value and the negative predictive value. This again becomes more important when you're using the diagnostic instruments mainly for either the screening or making a diagnosis, when you're comparing with a standardized criteria or the clinical diagnosis. And the other issues becomes important is the availability of the translated or the adapted version of the scale. So these are the factors which should be taken into account when you're selecting a scale for your study. Now, again, when we try to understand the different scales from that perspective, we have the diagnostic test and the screening test. The diagnostic test, they provide definitive information about the presence or absence of a target disease or condition. For example, you want to assess diagnosis of schizophrenia. Although you clinically diagnose schizophrenia by whatever knowledge you have, the ICD-10 criteria you are using, but for your study, you want to use a structured instrument, use the structured questionnaires to be sure that the diagnosis is clear. So maybe you end up using something like Mini or Mini Plus or Mini 7.2 or 7.0.2. So accordingly, you will choose one of those instruments to make the diagnosis for your study group. Because if you say that the diagnoses are made only by ICD-10 criteria, still some reviewers may raise a question and your paper may get rejected. So always a clinical diagnosis should be supplemented by use of a structured instrument to confirm the diagnosis in the study in which you are planning. For example, you are planning to study the quality of life of patient of schizophrenia. Your colleagues have diagnosed the patients as having schizophrenia, but for study purpose, it's always still better to use a diagnostic instrument to confirm that diagnosis. So that is where you need to understand that. And again, you say that the patient did not have any other comorbid psychiatric disorder. So how did you rule that out? Again, the so-called structured diagnostic instrument will come in, because these instruments will have not only the structured questions for one particular diagnosis, but a host or a group of diagnoses by which you can say that I've ruled out or ruled in this diagnosis or other things. For example, if you're making a comorbid diagnosis also, if you have used Mini Plus, it is still acceptable that yes, they have used Mini to make a comorbid diagnosis. So that's where it's important when you're talking about the diagnostic test. And the screening test, these are the less definitive tests compared to the diagnostic test, and these are useful in using in a larger scale. When you're in the camp setting, you want to screen somebody, or in the community setting, you want to do an epidemiological study, you initially want to screen people. And these are usually less time consuming. Now let's again come to this example that you want to assess depression in medically ill. So which scale are you going to choose? Anybody is again free to unmute and speak. Yeah. Yeah. Please go ahead, anybody.
Hospital anxiety depression rating scale.
Hospital anxiety depression rating scale. Okay, fine.
Diagnostic scale, sir. Diagnostic scale of depression in medical ill will be appropriate.
Okay. So diagnostic scale so which scale are you going to use there? Okay. Now let's try to understand this. That do you want to use the same ICD-11 criteria, DSM-5 criteria, or you want to use Mini, PHQ, BDI, or HAMD, or the HDRS? So again, we need to understand here. For example, that is where it becomes very, very important when you're trying to, let's say, let's first start with this rating scales. Now, PHQ is based on the DSM-4 criteria. It has 9 items, takes those 9 items into consideration equivalent to the DSM, each criteria, and then you try to rate them based on the duration for which the symptoms are present, and then you make a diagnosis. Whereas in BDI, you have items which are not equivalent to that of DSM-4 or 5 criteria. They have items more than that, or maybe there are 1 or 2 things which you can always say that these are not covered by BDI. Same holds true for SDRS. Now, in a medically ill patient, if you want to choose between SDRS and BDI, what would you prefer? Anybody? Yeah. So,
BDI, sir.
Very good. Why are you going to choose BDI?
Like some concerns of the patient which are not in the general depression part will come in that BDI.
So what we need to understand when we compare BDI and SDRS, SDRS has a lot of somatic symptoms which may overlap with the symptoms or the manifestation of a physical illness. So SDRS is not as good a scale as BDI for assessment of depression in medically ill, or simply saying that BDI have more cognitive loading. Cognitive means not the neurocognition, but the depressive ideations have much more higher representation in BDI compared to SDRS. So from that perspective, the overlap from the medical illnesses symptoms will be less picked by the BDI, so the accuracy with BDI may be slightly better. That's where you need to understand when you are going to choose one of these. Similarly, if you want to say that again, I diagnose with ICD-11, DSM-5 or Mini. Now the question here again comes in is, who is going to do this? ICD-11 or DSM-5 or Mini? Whether you want to do it or your medical colleagues want to do it. Now the next question comes that suppose your physician colleagues want to use this scale. They themselves want to use the item, this scale. Suppose a MD resident from other department where you are the co-guide, he wants to use the scale. Now, what are you going to advise him? That which scale to be used or which instrument to be selected? Anybody?
PHQ.
Yeah? Yeah, please go ahead.
Patient health questions.
Yeah. So PHQ 9 or maybe BDI may be more appropriate here if you want to do that. But you want to stop the research there or you want to do anything further there? What are you going to tell the resident with whom you are now working as a co-guide, what is to be done next? Yeah. Anybody? So there's something called as two-stage screening. For example, the physician or the resident uses PHQ 9 and Beck depression inventory. You tell him that these are the cutoffs for the scale. Let's say if somebody scores about 10 in the PHQ or above 14 in the BDI, please bring the patient to me for clinical evaluation. From that perspective, if you're collecting the data of 100 people, maybe in his screening about 40 screen positive, and you evaluate them clinically based on Mini or whatever criteria you use, and you make a diagnosis of definite depression in 30. So ideally, the manpower which was required, like a psychiatrist evaluating 100 patients, was not used. Only 40 were evaluated by the psychiatrist, and the diagnosis was confirmed in about 30 cases, and the 60 patients were not actually evaluated by the psychiatrist. So these are the people who screened negative. So we did not assess them further. That is the limitation of this study. So it is still better than just doing a screening by using PHQ or BDI. So it is better than that. Your study strength will be much better. The acceptability of the new paper will be better, that yes, the psychiatric assessment has been done by a mental health professional, so they have confirmed the diagnosis at one level. Otherwise, you may receive just 2-line comments from the reviewer or the maybe editor. The study is just based on the screening instrument, which was done by a non-psychiatric clinician, and so that the so-called the diagnosis represented here is not equal to clinical diagnosis. So your paper gets rejected, the 2 years of thesis work or whatever is done, or the research work which has been done is rejected, and you think, where did I go wrong? So that is where you need to know how you are going to make your study more robust that it can be generalized. Now, if you say, no, I am going to go and sit in the medicine OPD or the endocrine OPD and evaluate all the patients, fine, well, you can go and do that, use Mini for all patients there, but that will be more labor intensive. It will require more time from you. But if you say the Mini was used by the junior resident in medicine, or let's say endocrinology senior resident, again, people will question about his training and his ability to pick up the depressive cognition. So from that perspective, you need to again understand, if you're evaluating depression in medical ill patients, still a better trade-off is a two-stage screening method, which is being talked about in the literature. Now, let's move further from here. Is what we are discussing is the screening instruments. So screening instruments, there comes some of the important understanding of the aspect is the sensitivity, specificity, the positive predictive value or the negative predictive value. How different scales function here. Because when you're going to choose the scale, you have to decide about this. So if you look at the sensitivity, it is the ability to detect a disease. So you are using a scale to assess whether the person has depression or not, PHQ-9. So what is the sensitivity? What is the specificity for the scale? So the PHQ-9 has sensitivity and specificity close to about 86% and 87%, both nearly equal there. So we'll discuss that again. So it's the ability, sensitivity is the ability to detect the disease, and the proportion of the disease that was correctly identified is considered with a true positive rate. So you determine the sensitivity by true positive divided by true positive plus false negative. So this is the sensitivity, that true positive divided by true positive plus false negative. Specificity, on the other hand, is the ability to test to detect no disease. So you are detecting the so-called true negatives. So the proportion correctly identified as not having the disease is the specificity of the scale. Now, all the screening instruments, when we are using or we are determining screening instruments, our aim is to have high sensitivity, so that if you want to do a second stage study, that how many are going to be evaluated by the second step per person, the sensitivity of the scale should be high, so that anybody who is considered possibly having depression also may be picked up, so that the person can again go further evaluation. So higher sensitivity is required. Whereas when you're looking for a diagnostic instrument, higher specificity is required, that somebody who does not have disease should not be diagnosed. So from that point of view, when you're looking for the sensitivity and specificity, you need to understand that sensitivity test rules out the disease, whereas specificity rules in the disease. So specificity means if somebody has a diagnosis with a very highly specific instrument, diagnosis is confirmed. With a highly sensitive instrument, somebody does not have disease, definitely he does not have disease. That's what we need to understand, the rule of snout and spin. Then comes the positive predictive value and the negative predictive value. So the positive predictive value is the proportion of the test positive results that are truly positive, and the negative predictive value is the negative test results that are truly negative. So again, here the calculation is slightly different, the true positive divided by true positive plus false positive. And in the negative predictive value, true negative divided by false negative plus true negative. So again, it's a trade-off which we are trying to make when we are trying to use different scales, or when these scales are constructed. So what we need to understand that these predictive values take into consideration the so-called prevalence of the disease, in contrast to the sensitivity and specificity, which are not influenced by the prevalence of the disease. And the positive predictive value and the negative predictive value look at the subject from the point of view that the test results being positive or negative, and they determine the likelihood of it being correct. That is, this is clinically useful. So high positive predictive value will indicate the better scale which you are going to use. And this, I'll leave this. Then the other thing which is used in the studies is the ROC curve. There are two ways to evaluate the so-called sensitivity, specificity, positive predictive value, and the negative predictive value of a scale. For example, you have used PHQ-9 in the same sample, and you have used Mini in that same sample. Now you want to evaluate the the so-called sensitivity, specificity, positive predictive value, and the negative predictive value of the PHQ-9 against the mini. So you can use different options, and then you can calculate all this depending on the diagnosis made on PHQ and how many people test positive on PHQ and how many people test positive on the mini. So that on that basis, you will determine the positive predictive value and the negative predictive value and so forth. But for certain things where you want to make a cutoff, let's say whether a person has stigma or not, or whether you want to say at what level you can say that above this, the person will consider to have something and not have something. So there ROC will come in, that it has a diagnostic ability as a binary classifier. So ROC plots the sensitivity of the scale as in the one axis, that is the x-axis, and the false positive rate in the, sorry, this is the x-axis and this is the y-axis. So when you look at this, the so-called ROC, the area under curve is this whole thing is the 100%. So if any scale has ROC or the ROC area under curve is higher, it means the scale has good psychometric properties. I'll leave it there. So the more the ROC, you are looking at the left side and the upper side, how much is being covered. More the area under curve, better is the ROC or the diagnostic ability of the scale, and you can, the trade-off at which you want to determine the specificity and the specificity of the scale, and this is where you will play on the trade-off. Anything the area under curve is less than 50%, then you can say that the ROC values are not fitting in well, and the sensitivity specificity are not very good for that cutoffs which we are trying to determine. So the determination of cutoff at which the optimal sensitivity and specificity is achieved is done by just playing or so-called evaluating the data by using different cutoffs and understanding the diagnostic accuracy of the test by evaluating the sensitivity and specificity under the ROC. Many people say that ROC should be used if at all you have the gold standard diagnosis, but as far as I understand, that if you have a gold standard diagnosis, you don't need to have an ROC data to be evaluated. So that is where you need to understand when many scales, that's why they don't describe the ROC figures. They will just describe the sensitivity and specificity and positive value and negative predictive value against the gold standard. And the ROC cutoffs are usually chosen according to whether one wants to maximize the sensitivity or the specificity for the test. And the ideal cutoff is one which picks up a lot of disease that is highly sensitive, but has very few false positive, that is high specificity. So that is what, again, every time we are trying to achieve with any kind of scale. So when you're choosing a scale for your study, especially when you want to choose, let's say, BDI, PHQ-9 or HDRS, you should look at which of these scales have high sensitivity, high specificity, or the ROC data available for the scale in that particular age group or that particular medically ill people or whatever you want to evaluate. If somebody has done those analysis, you can make use of that data in selecting your scale, and that can strengthen your study when you're writing your paper or when you're writing your protocol. If you put that this scale has been used in this group, these are the valid so-called psychometric properties have been actually evaluated in this particular group and they've been found to be good, it is going to be very useful. The other measures for scale are the reliability and the validity, because that's where again the whole issue comes in, that with the scale which you're using, what is its reliability and the validity. So we understand reliability, it basically refers to the consistency of measure which you are evaluating, and we have three types of reliability, that is the test-retest reliability, the internal consistency, and the inter-rater reliability. The inter-rater reliability is usually used when the so-called scale is being used by the two raters to evaluate a person. So it is more of a, if a clinician is assessing a person, two persons, or the clinician is assessing one person, two clinicians are evaluating one person, you are evaluating the inter-rater reliability of the scale. The internal consistency, on the other hand, indicates how much each item is correlated with each other, and the test-retest reliability indicates how much is the consistency of the scale if you use more than once. So the test-retest reliability is that how if the scale performs over time, and it requires using the scale at least twice with a certain gap between the two assessment and then looking at the test-retest correlation between the two sets of scores. Usually Pearson R or the Pearson correlation coefficient is calculated for that. And the test-retest correlation of more than 0.8 is considered to indicate good reliability. And this is useful for constructs which are consistent over time. For example, intelligence, self-esteem, or the personality features. These are consistent over time. So these are the kind of measures for which the test-retest reliability is calculated. But you will see that in literature, many scales for which you are using commonly, the test-retest reliability would have been calculated. Here, the assessment period between the two assessments will be very short. Let's say 2 days, 3 days, 5 days, so that the person's symptoms or the features which you want to evaluate, the so-called the area of interest which you are evaluating, has been consistent over the short period of time at least. When it comes to internal consistency, as I said, it looks at the consistency of people's responses across the item on a multi-item measure. So in general, all the items on such a measure are supposed to reflect the same underlying construct. So the people's score on each item should correlate with each other or at some level. And if these different items are not correlated much with each other, then it would not make much of sense. But again, you need to understand the multi-item questionnaires can have different construct included. So there are different domains being constructed. So the items may correlate in a particular domain, but may not correlate in the other domain. So that's a factor again, which you need to understand when you're evaluating the psychometric properties of the internal consistency of a scale. So the internal consistency is usually evaluated by using the split half correlation. And this split half correlation is basically that you divide the number of items of the scale into two groups by using any kind of formula, that first 10 and last 10, or the odd and even, and then you look at the correlation, how they work out. But usually with the computer software, the computer itself chooses the number and they does it for the computer the software does it for you. So nothing much to worry about that. Yeah, somebody is raising hand. Yeah, somebody wants to ask anything. Should I continue?
Yeah, please continue, Dr. Sandeep.
Yeah. So, however, the most common measure for internal consistency is Kornberg alpha. Again, this can be always obtained from the SPSS or whatever software which you use. It again basically evaluates all the so-called split half correlations. For example, if the scale has 10 items, so there are 252 permutation combination which can happen. So the 252 split halves are calculated and mean of that is drawn. But not actually that is how it is done, but that's how the software does it. Again, the 0.8 internal consistency is considered to be the Kornberg's alpha 0.8 is considered to be having indicates that the scale has good internal consistency. Now, what is again important, that suppose a scale which you are using does not have the internal consistency values for you. You can always evaluate the internal consistency of the data collected for your own data. Just that you can say that the internal consistency was XYZ in my data. So that itself can again be very helpful in at least conveying the message to maybe the reviewer, the person who is reading, that how your data or how the items performed in your study. The inter-rater reliability is evaluated for the scales or instrument that involve significant judgment on the part of the observer or the rater, and that how the different observers look at the same findings or how they judge that. So usually the inter-rater reliability is judged by like recording a video of the patient when XYZ is interviewing the patient, and then two independent raters are asked to look at the video and then do their ratings, and then their ratings are compared. So, for example, if you want to determine the inter-rater reliability at your center for a particular scale or something, that is what you need to understand. How are you going to go about? It's not just that one person is interviewing the patient and the other person keeps on recording the ratings. It could also be possible that rather than having a video recording, if that is not feasible, that one person interviews a person and the other two are observing based on whatever the interview is happening, and then they are doing the rating. So again, in the inter-rater reliability, you calculate the Cohen's kappa, which is again as assessed for the categorical variable in terms of presence or absence. So the diagnosis is made as present or absent, so you calculate the Cohen's kappa there. Then comes the validity of the scale. So validity is the extent to which the scores from a measure represent the variable they are intended to measure. Now, let's try to understand that if you are using a scale to assess depression, whether it accurately measures depression or not, we want to look at, or it is beyond depression what is being measured in the scale. So that is where you need to understand how valid is your scale. So the commonly talked about validity are the face validity, the content validity, and the criterion validity of the scales. So the face validity is the extent to which the measurement method appears on its face value to measure the construct of interest. Suppose you want to again measure depression. So if the items include sadness or mood or the anhedonia, and this a scale which includes these items would be considered to have good face validity. And usually this is, again, the face validity is very informally assessed. There are no statistical methods used, and it's basically based on the judgment or the intuition of people who are determining the face validity. So if a scale only has a face validity, okay, it has something, but not as good as having other kind of validities, which I'll be discussing. So the content validity is the extent to which the measure covers the context, the so-called the construct of interest. So if you're evaluating depression, whether the scale covers all the 9 criteria of depression or not, has that been covered or not, that is what you have to look at, that how much is the coverage of that scale. So that is what you are looking at, the content validity. And the criteria validity is that the extent to which the people's score on a measure are correlated with other variables, so that known as the criteria that one would expect them to be correlated with. I'll be again discussing this further. So that you want to construct a scale to assess, let's say, quality of life for patients of depression. Now you want to, this is a scale you are planning to construct. So what are the factors, as we were discussing in the previous presentation, which can affect the quality of life? Maybe the different factors in terms of the severity of depression, the disability, dysfunction, or if you can use another quality of life scale to assess the so-called criterion validity for the questionnaire which you are developing. Now, there we talk about the different kind of validity. There is the concurrent validity and the convergent validity. The concurrent validity is the criteria is measured at the same time as the construct, and the criterion validity is referred to as concurrent validity, in that sense that you are assessing the quality of life, the depression scale you are developing, and then you're looking at the correlation with the severity of depression. So higher the severity, the presumption would be the lower should be the quality of life. If that kind of a correlation is not emerging, you can say that the scale has lower concurrent validity. And similarly, for the convergent validity, again, you're looking for the correlation between the 2 quality of life scale, that you're using a generic quality of life scale which has been used earlier in the depression, and now you're constructing a new scale. So you're looking at the association between the 2, how do they function? Whereas the predictive value, the predictive validity is what that you are using the particular scale now, and based on that findings, you are going to say how it is going to predict the future. So the future assessment. So when future we are going to assess the patient for the second time, based on the baseline finding, you can say that what would be the outcome. So for example, the simple thing which we understand in schizophrenia, that for example, the longer the duration of untreated psychosis, poorer is the prognosis, the poorer is the outcome. So that is based on the similar kind of assessments. The discriminant validity is that something that you are using another scale which has a totally opposite concept or have no correlation. So if you are just looking at the relation between the 2 scales, they do not correlate, or if they have a correlation, it is in the opposite direction. So that again indicates that these 2 variables do not interact with each other. Then comes the other kind of validities, which again becomes important in scales when you are using scales in a different cultural background, or when you are using the scales which have been developed at different places and you want to use in your setup. That is the conceptual validity, that the instrument which is measuring the things at the theoretical construct which has been measured in that one particular culture, is it same in your culture? Is going to be the same or not? And the semantic validity is that the so-called the translated instrument which you have developed, is it maintaining the same meaning, or is it conveying the same thing as the original scale or not? And similarly, something is talked about the technical validity. This is the method of assessment, which is that where you compare the functioning of a scale in each culture. For example, the self-rated instrument assume literacy, which may not be high in India. So PHQ-9, the validity, so-called the sensitivity specificity, which is reported in US or UK, that may not turn out to be same in India, where we have so much of variance in the educational level of our population. So that is what we need to understand. Now, so for selecting a particular scale, you need to understand how frequently the scale has been used in the past, what kind of population it has been used, and has the instrument been translated, and has it been adapted, and has it been validated locally or not. These are the important aspects, again, which you need to consider. So I'll just briefly run through this, maybe another 5 minutes about the translation and adaptation process. Sir, can I go ahead?
Yes, Dr. Sandeep, I think.
Yeah, 5-6 minutes. Yeah.
Thank you.
So when we talk about the translation and adaptation process, again, we need to understand the scales developed in one culture may not turn out to be the same in the other culture. So, the English which we understand, the person from Britain or England, US may understand, may not be understood here, and the cultural factors will make a lot of difference in understanding that. So once we need to understand that is where when you're looking for evaluation of a scale, okay, I want to translate, it should not just be a translation, but it also should involve the adaptation. So the language, when you're looking at the translation and adaptation process, you need to understand that the language of the scale should be such that is understandable to the study group. That you want to use a self-rated scale in Indian population, they should be able to understand that level of language, that the meaning of the scale is actually conveyed to the person. Otherwise, because it's an MCQ, so we all have done MCQ in our life, so we know that for some MCQs we don't know the answer, so we take a choice, tukka maarte hain, kuch bhi laga do, dekha jayega. So that is where the patient may end up doing it otherwise. So that is why you need to frame your questions in such a way that those are culturally and socially accepted, and they are also measuring the same psychological parameters. So the translation process and the modification process should keep this in mind, and when you're trying to do that. And the adaptation process, again, you should take into understand something like the free translation, that you have to be true to the meaning, but not the literally that you have to use the same word when you're adapting a scale. Now, I'll just take 1 or 2 examples here. Now, can anybody tell me a Hindi translation or any other translation for this item now? Let's say, when X speaks in a strange or nonsensical way, I tend to quarrel with him. This is an item for a particular scale. Now, you want to convey this to your patient group. How are you going to convey that in your language? Maybe anybody who has some Hindi background can give me a option for this.
Sir, you want me to translate that into native language, sir? My native language, like that? What?
Okay, you can translate your own native language, or maybe Hindi, so that I understand.
Okay,
you can translate it to your own native language. Others can help you whether you are doing it right or not.
Yes, I'll speak. Try to translate in Hindi, sir. जब कोई मेरे से जब कोई मुझसे इस तरह से पेश आते हैं जो मुझे अच्छा नहीं लगता, तो मैं उससे झगड़ा करने लगता हूँ.
हाँ. So is this okay for everyone? Is this okay for everyone? Yes.
Okay, sir. Okay, it's okay.
It's okay.
No, sir.
Yeah. Give your views.
The meaning, I think, has changed a little, where he's assuming that Dr. Sanjay has said he quarrels with me rather than I quarrel with him.
Okay. जब कोई मुझसे क्या बोलते हैं? I don't know what strange to say, sir.
No. Let me again make things simple to you. Here, this is a scale which is to be filled by a caregiver. Here, X stands for the patient. Okay. Now, I have given you some background. Now, can you translate it again? You're muted. You're muted.
Can I tell, sir?
Yeah. Sir, please.
Yeah, go ahead.
Go ahead, Dr. Ramesh.
कोई मुझसे बुरा बात करे तो उनसे मैं झगड़ा कर सकता हूँ.
So strange and nonsensical way is being equated to bura baat, isn't it? Is that conveying the same meaning? Is that conveying the same meaning? That is the basic problem.
No, exactly.
Yeah. So that is what exactly our residents do, or when we use in thesis, or when we do apply the English scale in our population, and we do so-called extempore translation. So extempore translation is done mostly by many people when they are using English scale in the studies which have not been adapted or translated, or they do not have a translated copy in their hand. So that is where there will be a problem. Now let's see at this. How does this make it? Can anybody read this now, and how many of you agree and disagree? To make it more simpler for the caregivers, I made it more explicit. Tell me, does it retain the meaning or not? That is what we are looking at. जब भी मेरा बीमार रिश्तेदार अजीब व बेतुकी तरीके से बोलता है, मैं उससे झगड़ा कर लेता हूँ. Is it conveying the same meaning?
Yes.
How many of you disagree?
Yes, sir. Agreed, sir.
So that is where you need to understand that you have to reach to the level, rather than writing X here. If I have written कि मेरा बीमार रिश्तेदार, I am just making it personalized for the person to understand the question, rather than, because for people in England or US, they can remember at the opening sentence X means your relative. But in India, if you write X, they will not understand. So every time maybe it's better to remind that X here means the sick relative which we are talking about. Now, let's look at this item now. I don't socialize as much as I used to because my mental illness might make me look or behave weird. Now, anybody tell me a word equal to weird? All of you use this kind of scales, isn't it? So how do we use it now? You want to convey weird. Ajib. Yes.
Alag, sir.
Alag. Yes. Now see, that is what exact problem comes in when you are doing extempore translation. So that is why there is need to develop the instruments. So like now you look at this sentence here which has been used for the translation. मैं पहले की तरह लोगों से घुलता मिलता नहीं हूँ. I don't socialize. Here I have added पहले की तरह, means I have tried to compare it with his pre-morbid self. Okay, क्योंकि मुझे ऐसा लगता है कि कहीं मैं मानसिक बीमारी की वजह से अजीब लगता या दिखता तो नहीं हूँ. Look or behave. Okay, अजीब लगता या दिखता तो नहीं हूँ. So that is where you need to understand that you are trying to convey the meaning as much as possible, and you are trying to be faithful to the question which is being asked. Otherwise, if you just keep on doing extempore translations, many of times the translations are wrong and whatever the scores you are getting would not make any sense. Now, I'll leave this here. For example, what is the word you use for stereotype? Now, negative stereotype. Now, you need to have a very difficult word to find out to use an equivalent to that. Now, if I ask all of you, do you understand the meaning of this word Rudiwadi? Many of you will not understand. So if I give this questionnaire to you, because you have to give one answer, you will be by force answering one of the tick. You will tick it without understanding. So that is where you need to understand when you are trying to develop scales, that you use different steps to understand the development of the adaptation and the translation. That is the forward translation, the expert panel backward translation, the pre-testing, and the cognitive interviews. That somebody has in the pre-testing phase, somebody who has fill the questionnaire, you sit down with him and ask, why did you give this answer? What do you mean by this? What have you understood by this question? And then doing the final version of the scale. So I'll stop here. Okay. Thank you, sir. Thank you.
Thank you so much, Dr. Sandeep. I think a large number of qualitative and quantitative aspects of scales and the scales, their psychometric properties will have a bearing on how we go about using the statistical tests and also about how we interpret the statistical results. So this was an extremely useful presentation. Thank you so much, Dr. Sandeep. There are a few questions, one or two, which probably because Dr. Dennis had to leave. I mean, if you don't mind, I'll start from there and we'll continue on to the questions related to your topic. Is that okay, Dr. Sandeep?
Sure, sir. I'll try to answer whatever I can. Yeah.
Yeah, I think this question is quite straightforward. I think the answer is yes. If you want logistic regression, we should be aware of the kind of relationship between dependent variable and all independent variable. I mean, I think the point there being made is that we should have a technical understanding of how this relationship is, this particular variable is likely to have an impact of, is say relapse, not relapse or something. We should have an understanding of, okay, this independent variable might cause a relapse or not. And then you kind of look at the strength of that association, the strength of that relationship through the regression analysis. So I wouldn't bother you, Dr. Gore. Yeah. This question, I mean, I think it was with regard to those model fitting, which is to be done before a priori or to be done, what is the point at which the model should be thought of? Ideally, how many models should be considered? How many variables per model?
Okay. Again, there are no, as Dr. Dennis was discussing in the beginning, it totally depends on how many variables you have and how many outcome variables you have pre-planned to be used in that study. Suppose you are using multiple scales in a study and you're using everything as an outcome variable. Suppose you are using psychopathology, you are using quality of life, disability, and let's say depression, all as an outcome variable. So then you have to predict or so-called propose all models for each of these things. So there is no fixed numbers. So it totally depends on how many scales which you are using and what can be the association between the different variables. So there is nothing fixed in that, but it should be that all this should figure in your aims and objectives and should be there in your analysis, or so-called the SAP, which Dr. Dennis discussed. It should not be the post hoc kind of a hypothesis. Once you have seen the results, you have done, okay, let me try this. That is something which is not acceptable.
The next question is from your presentation, Dr. Grover. What the inter-rater difference is acceptable?
Again, 0.8 is the cutoff for everything. When we talk about the Cohen's kappa also has the good Cohen's kappa, 0.8 and above is considered to be good.
Another question is, when we do the language translation of the scale, do we have to do validity, reliability, Cronbach alpha again?
Yes. So once you are doing the language translation and everything, it's always good that you not only just do validity, reliability, Cronbach alpha and other things, but also do something called as cross language equivalence. So that is that the same group, that is where people say that you use the so-called scale in the bilingual people, that somebody you have translated a scale into, let's say, from English to Hindi. So you use the scale, now you give the English version of the scale to a group of people today, and then the Hindi version of the scale to them again, maybe after a few days, and then see how they perform the same scale in the different languages. So cross-language equivalence needs to be done in addition to the evaluating the reliability, validity, and the Cronbach alpha. Usually validity is not evaluated because every instrument which we are doing may not be a diagnostic instrument. So the validity is talked more in relation to a diagnostic instrument, but reliability needs to be evaluated. And because if you are doing a self-rated instrument, you may not do an inter-rater reliability, but the other reliabilities needs to be done.
Another question, I think Dr. Smita wanted some kind of a repeat this description of construct validity.
No, the construct validity is, as the simple fact is that the measure which you are trying to measure, or the thing which you are measuring with this particular scale, is the scale doing that or not, is something which you are looking at. So from that perspective, that is what we understand as the construct validity of that scale. So for example, you want to construct a scale to evaluate, let's say, stigma. Now the questions should be framed in such a way that all the questions are evaluating stigma at independent level, and they're conveying the same meaning. If you look at the literature, the most common scale which has been so-called criticized or discussed in terms of the construct validity is, people talk about the 5-factor personality questionnaire. Now there the people talk about that some of the questions are such a way that they actually do not mean that they are evaluating a particular feature of that personality, or the so-called the domain in which they are fitting. I hope I have answered your question. If you have anything further, I can still try, Dr. Smita. Yeah.
Dr. Smita, do you want to seek any clarification on that?
So do we use Cronbach's alpha for construct validity?
No. See, when we are evaluating the validity, yes, the measures, I'm not very sure about you doing the Cronbach's alpha there. I just need to check what is the statistics there for the validity. It's not the alpha value, if I'm correct. I need to check that.
Yeah. If I can fill in the core, see, Cronbach alpha is actually a measure of internal consistency of the tool.
Yeah.
It's not, so now when you're measuring construct validity, let's say you may got a depression instrument, you developed a depression instrument, you want to see another depression instrument, how well they actually agree with each other. Okay, so there you're mentioning, look how Dr. Grover mentioned, you're looking at convergent validation of the tool. It kind of tells you that, yes, this is really measuring the quality of depression because the ratings on this agrees with another measure of depression also. So you confirm that. There you're looking at the correlation between the two rating scales. Okay, and Cronbach alpha would not come into play there. Okay.
Can I add something, sir?
Yes, Dr. Indu. Yes, go on.
Cronbach's alpha, as mentioned, is a measure of the inter-item correlation, how each item correlates with the others. But construct validity refers to whether the questionnaire assesses all the theoretical constructs which are related to that particular concept which you are assessing. So for that, you try to see, it can be confirmed by factor analysis. So you can go for an exploratory factor analysis and a confirmatory factor analysis. Of construct validity, what is needed is factor analysis. So I am developing I have developed a questionnaire for domestic violence. So I have various constructs in mind: physical violence, so sexual violence, psychological violence. So I can, with the questionnaire, I can go for a factor analysis and see whether the items which I have 36 items maybe. So I can go for a factor analysis and thereby see whether these items fall under specific domains or factors. So that is a statistical process which the computer does for you. And then you can see whether I had in mind that my items would fall under psychological, physical, and sexual violence. Whether these domains are, the items are falling under that you can cover by factor analysis. So that is the method. For construct validity, what is needed is factor analysis.
Okay, can I continue there? The more simpler thing to remember that for validity, you either do correlation analysis or you do the Pearson and the kappa statistics. You usually don't do the Cronbach's alpha value there. As Dr. Indu said, factor analysis, again, factor analysis will again have other kind of presumption that you don't know which factor is going to emerge from your data also. So it is not necessarily you have predetermined factor to start with. These could be not predetermined factors. By factor analysis, you actually determine the factors, that how your scale fans into different factors. So that is, the factor analysis will have both the kind of things which can be, by factor analysis, you can prove that the domain which you thought is stable or not, or by factor analysis, you can actually construct the new domain.
Thank you. Thank you.
Probably what Dr. Indu particularly probably meant, Dr. The confirmatory factor analysis. So you know that a depression rating scale has got commonly 5-6 factors. Okay. Now your confirmatory factor analysis can try to look at whether such factors, you've got something to look at. You'll see if they are actually matched by the factor analysis that you will do with the scale. I mean, but that said, I mean, more often you just want to see if the measure of the scores that are coming on that scale is matching with similar performance on other scales also. Okay. Or for example, another way is, you can do divergence also, in the sense, if you got a rating scale of depression, it is definitely going to be, for example, not agreeing with the rating scale of, very high
Happiness.
or a lot of happiness or happiness, or I'm extremely satisfied with my life. If you have a satisfaction questionnaire, that questionnaire is not going to match with the depression if somebody is having high on depression. So if this score shows high on depression, but it goes low on satisfaction, that's again you are saying, okay, the construct of depression is, whatever, the illness is actually captured in this scale. So there are different ways in which you're going to go about construct validation. Okay, but I mean, it's something that as you keep reading about this topic, it'll probably get easier and easier for you to probably appreciate the different measures you want to use at a particular instance to confirm construct validity for that context.
Thank you, sir.
I think there is one question which has been left, that so if we want a scale in local language, that itself needs to be done as a separate research article. Yes, it has to be done as a separate research project, not just a research article, but a separate research project. It itself requires a research methodology, and that is where you need to write the separate protocol and do the research separately and then write it. Or the main research which you are doing, it can have a subgroup kind of a data analysis, or there you need to commit that additionally I'm going to do this in this study. So it totally depends on how you want to approach, but ideally it should be a separate research project.
There is a question in the Q&A box.
Yeah. Can I read that, Dr. Indu?
Is permission required to use the HATS in a hospital-based population? HATS is available freely as a PDF. I understand that licensing is required for a publication. Do advise.
See, again, that is what I've said, that for when you're using in a clinical practice, things are different. Whether you want to, there the whole purpose is clinical monitoring. There are no major issues. But when it comes to publication, again, if you do not have the license or the permission from the copyright holder, anytime you can fall in trouble. That is the basic thing which you need to understand. So for any kind of research purpose, it is always better to seek permission from the copyright holder.
And the good news is most often people will agree to it. Okay, it's just you need to do them. Most people are happy if you just contact them and you have that with you, then it's pretty ironclad. It's very rarely, if it's a highly funded study or even funded study, they've got a cutoff, about something like equivalent to some $30,000. There's some equivalent to that. So if they feel the funding is much more than that, they may ask you to pay something for that. So very often, feel free to just write to the author. Very, very often they will actually going to say, it's all right, go ahead and use it and keep me informed about the results or something like that, they will say. So most people are that their instrument is actually being used in more studies. Okay. Except maybe highly funded studies, you may have to pay. So, but it's good to get that permission up front.
Actually, the whole translation and adaptation is a total separate presentation. So I just rushed through, but I think that is one of the important presentation which should be discussed in detail maybe sometime later.
So Dr. Srivatsai, I think your question is answered, that we need to inform the copyright holder before starting the scale if you are using it for research purpose. Yeah.
Yeah.
Now I think this has been very helpful. There's one more. Could you please throw some light on intra-class coefficient?
Yeah. Again, the intra-class correlation coefficient is again usually used when you're evaluating the psychometric properties of a scale. And here again, when you're trying to evaluate the so-called test-retest reliability, that is where it is used, or it is usually used there. That again, it's equivalent to the so-called Pearson correlation coefficient. It's slightly more complicated than that, but again, this the software is going to do that for you. But again, you need to remember that it needs to be done for evaluating the test-retest reliability.
You are muted, sir. Ashok, sir. Ashok, sir, you're muted.
Yes. Thanks, Dr. Yeah, there's one question. We'll probably close the session with that question. What is the ideal sample size for translation and adaptation?
Okay.
I think it basically means
again,
for test, retest, and all that. What would be the?
Yes. So that is where if you're doing test, retest, and that kind of a data, depending on the length of the scale, but usually a sample size of 30 is the minimum which you should consider. But if you plan to do a factor analysis, again, you need to remember that number of items into 10 times. So if you have a 15-item questionnaire, maybe 150 should be the sample. So that is where if you're planning to do a factor analysis, at least the ideal is 10 times or at least the 5 times. So 75 to 150. But if you just want to do test, retest, and other things, it's minimum sample size of at least 30 is required.
These are very important points, Dr. Grover, because one possibility is, we might kind of, from the research capacity building committee, not immediately, probably time to come, initiate studies which might actually look at adaptation of common rating scales for all South Indian languages, so that it kind of really starts off making the researchers' life easy in South India. So now I think a lot of what you said, and it's extremely relevant. Yeah, thank you so much. Dr. Rekha, your hand. Sorry, Dr. Grover, are you okay to take one more question? We'll end with
Yeah. It's okay, sir. It's okay.
So when we are doing our thesis and all, we use some mini scales like that only, mini plus. We ask the author, it's a copyrighted version, they'll give permission. But what about the translation when we are writing in the research paper or in thesis? Do we have to mention that it has been translated in the local language, or what is the way to go about it?
See, ideally, usually if the scales are self-rated, and if these are not translated, the reviewers usually take an so-called negative view about your study. I'll put it very, very simply there. If it's a self-rated scale, if it's a clinician-rated scale, still people may still raise question about the so-called translation and adaptation. So you can still escape from the reviewer's hand if it's a clinician-rated scale. But if it's a self-rated scale, you'll always be trapped in terms of the adaptation and the translation of the scale.
Thank you, sir.
This has been an extremely useful session, Dr. Grover. Thank you so much. Really appreciate your staying over extra time to help out the trainings. So thank you so much. With that, we come to the end of this session. The next session, which will be on 1st of August, I think Dr. Dennis will talk about sample size estimation for varieties of designs, and also Dr. Tenarasu will join us to discuss about working with a statistician. So that's the topic for next session. It will be on Sunday. I know we have sent out a request to all of you to consider weekdays instead of Sundays, and what is your option. A lot of responses are coming in. Many others are still to respond. Please let us know about it. But as of now, the 1st August session on Sunday will go ahead. Yeah, so see you all in a week's time. And of course, in that session, and there won't be any change to this, definitely the research quiz will be held on the 1st August. So that will be this first session, followed by sample size estimation by Dr. Dennis. Then Dr. Tenarasu and Dr. Dennis will have a dialogue on working with the statistician. And thank you all for joining. And again, a special thanks to you, Dr. Grover, for joining us today.
Thank you, sir. Thank you.
Thank you, sir.
Thank you all. Good night. Yeah, we may not have any other meeting of the RCBC today. We will communicate again over WhatsApp. Yeah, thank you all. Thanks.
Thank you, sir.
Yeah.